record, share screen, advance. I share everything. Stop. Okay, share. Okay, I'm just gonna do a brief introductory. Hi guys, I'm Joey Issa, OZEP on Discord. So this will be the recording. I'm gonna cover CSI 2110. I am a student, so if I get anything wrong, I blame it on either being tired or like having not covered this material in like 4 months. Question? It will be posted to my YouTube channel and also to uOttaHack's channel, I think. So you will be able to find it. And I'll give you the link to my Discord later. Going forth, if you have a question that is on this material, feel free to ask, but I will look up periodically and then select the people who has questions. I will also ask you guys some questions to make sure you are engaged with the material and you actually understand what I'm saying. If you have questions that are not on this material and it's like more like in depth, you have like an algorithm that you want to implement and you're trying to see like, oh, is this possible? Please leave those questions till after the session. I want this recording to be quick and concise so that if you guys have like an hour or two before the exam and you need like a brief like overview of the top concepts, you can just watch this video. That being said, I'll get started. Any questions just off the start? Anything? Okay, we're good to go. So the first section is going to be everything you know about big O. Big O is like one of the first things you covered. I'm going to assume that you already know its usefulness and you already know why we want to calculate big O, because that's just the basics. What Prim might ask you is actually just like going into what is the big O of this algorithm? What is the big O of this section of code? So to start off, we're going to have the basics. So we know if you graph this out, it's actually much easier to see. But O of a constant is preferred over O of log n. O of log n is preferred over O of n. O of n is preferred over O of log n. And O of log n is preferred over n squared. It keeps going the more growth an algorithm has. What a great way to actually like visually see this is if you graph each of these functions. So you can see like O of constant stays at a ready pace. Like to calculate anything through O of constant is very fast compared to O of log n, which is some sort of function like this. And then O of n is going to be a straight line. And then you can keep going O of log n, you can keep going through that. You know that O of n squared is also just very big, something like that. They all kind of meet, but you want to look at the worst case complexity. So you mostly focus on what it does when you get closer to infinity. So yeah, that's just the basics. This is stuff you need to know. So if he asks you a question like, okay, which is preferred, O of n or O of log n? You would know to select O of log n. And if he asks you, is something like this, is O of n O n log n, just as an example. Anybody know the answer to this? Anyone care to take a guess? Well, O of n can fit within O of log n. So it's a higher year question. He might not ask you something like this, but it's good to know. If the function is greater and you're comparing it, then you can say O of n is the big, like it's a big O of log n, or O of log n is a big O of n. That's just like a brief example to show you like, if you have a smaller function, you can say it's a big, like you can say that a bigger function is its worst case complexity because it won't reach the roof. So like you can see it here. This is O of n, right? And then you have n log n. It's just going to be a bigger function. You can say that even though it's not really accurate to say that this is its big O, you can still say that it's its big O. So he might ask you a extra question like that. Just be wary. I would say review these concepts a little bit more deeply than what I'm going at them with. Okay, now we have the first question. He's gonna, most likely during the final, you're gonna encounter some questions like this, where he gives you a piece of a segment of code and he's like, what is the big O or complexity of this algorithm? It's very, very simple. I'll go through the first couple slowly and then I'll pick up some pace. So right here you have you're counting a sum. Your sum is equal to 0. Okay. And then you have your first for loop. This loop is going from 0 to 10. And then you're incrementing I iteratively. So I will be from 0, 1, 2, all the way to 10. And then you're just incrementing the sum by the same like margin, by 1. That part's not really important. And then the function returns and, everything works out. Well, you can see that this function is only going through this for loop 10 times. So O of 10 is also O of constant, which is, we call it O of 1. So that is your first quick example. This question is really easy. The next couple I will cover are much harder. Does everybody understand like that, just the initial bit? Perfect. Okay, now you have something a little bit more tricky in concept. So you have a first for loop. I highly suggest you go line by line like I am. Analyze every single bit of this code because he might increment somewhere else and you haven't paid attention to it. So you skip it and you say like, oh, it's O log n squared, or it's O n squared. Instead, it's O log n. So I'll go slowly for this one. So this I increments from 1 all the way to n. Then we said j is equal to n. Okay, while j is greater than or equal to 1, we will go through this while loop so many times. You can see here, j is exponentially decreased. What I mean by exponentially decreased is that if you have a j that is equal to 16, 16 divided by 2, it's now 8, it's halved. So if you would graph that as like an actual function, you have 16, right? Let's just pretend this is 16. So it goes from 16, it goes to 8. Well, it's the opposite way. It goes to 16, then 8, then 4, then 2, then 1. Like you can see, it's if you graph this out, it's kind of exponentially decreasing. In terms of those questions, you would call it log n, because log n is taking, so log n, log base 2 n is the same thing like, okay, what's 2 to the power of n going to be equal, right? Because you're factoring it out. So in this case, we're exponentially decreasing j. So j goes from 2 to half of n to a quarter of n, and it keeps going. So in this case, this complexity up here is O of n. This section right here is going to be O of log n. And since these two for loop, like this while loop and for loop, are embedded within each other, you would multiply those complexities to O of n log n. And that is your solution for this example. Does anybody have any questions in terms of like, why is it O log n? No? Okay, perfect. Continuing forth. Multiplying this is just a simplified version of what actually happens in math. I think it's the method Prim told you to do, so I'm going to keep it at that. Okay. Now you have another question. We're going to cover a lot of big O's because he might trick you a little bit with them. So, okay, you have a sum, doesn't really matter. Then you have I. I starts at 1. I starts at 1. Just going to do I. Sure. Okay, well, I is less than or equal to n. So we're going from I all the way to n. And then you have the second for loop that has j. J starts at 1. While j is less than or equal to 100, you increment the sum, does not matter, and then you plus 2 to j. So j is plus 2. And then at the end here, you have I plus 1. So since these are like, okay, these are linearly incrementing. That means it goes from I, let's say I 0, 1, 2, 3, 4, 5. It's very linear. So it doesn't have any funny functions relating to it. And then you also have j. Even though j is plus 2 and it's not plus 1, it's still a linear function applied to j. So you would say that this would be like if this went to O n, this would be log of O of n. But you can see here, j goes from 1 to 100 linearly. That means at max, like its worst case, it's gonna go from 1 to 100, always. So in terms of that, that would be O of 1, or which is like O of 100. O of 100 and O of 1 have the same worst term complexity because it's just constant time. And then you have I, or you have the first loop, which goes from 1 to n. And you see here, I is incremented linearly. So it's just going to actually go from 1, 2, 3, 4, all the way to n, which you can associate with infinity. So that is going to be O of n. So then O of constant multiplied by O of n is going to be O of n. So that is its complexity. Okay, I'm going to change to black. Okay, now these are just kind of solidifying the previously covered topics. You have a simple while loop. It goes from I, which is equal to 1, all the way to n. And you can see here, like multiplication and division are not linear in terms of like when it's applied to a number. So whenever you see a multiplication or a division, think, okay, this is not going to be a simple linear function. It's going to be exponential. And like you think exponential, you think e to the power of x, right? Or 2 to the power of x. You should also think inversely log. So in terms of this, if you see anything multiplied, your head should, like it should just pop up. Okay, this is going to be O of log base 2 of n. We get the base 2 because that is what's applied to I. Okay, and that's as simple as that. Any questions for Jet? Yeah?
Can you just explain how that's O of log 2n again?
Sure. Okay, perfect. So this is going to be I to infinity, let's just say. 1 to infinity. We can associate n with infinity. Okay. I is going to be less than or equal to n. Okay. So we start off our I value, we started off with 1, right? And that's like your first iteration. Then we have I is equal to 2, second iteration. I is equal to 2 times 2, 4, third. You go all the way. Let's pretend I is now, well, okay, I can just do I is equal to 8. I is equal to 16. And then continuing forward. You can see here, like instead of it going linearly from 1 to 2 to 3 to 4, you're skipping steps. So you go from 1 to 2, 2 to 4, 4 to 8, 4 to 8 to 16. You're like skipping 4 at certain times. You're going to be skipping half of n maybe if you keep going with it. If you would graph this function, like if you keep going and graph it, you're going to see like this growth is exponentially like increasing. Sooner or later, you're going to have 50 and you're going to multiply 50 by 2. And now you're going to jump by hundreds. So in terms of why this is O log n, if your value that you're iterating through is exponentially growing, that means the loop is exponentially decreasing. And I like to associate any exponential functions between two ways. You know that division and multiplication are related, right? You should also think in your head that exponentials and logarithms are also related. So that is why it's kind of essentially log base 2 of n. Does that answer it enough? Sort of? Okay. Yeah.
Question?
Sure.
Like in this case, if n was like 100 or something like that.
If n was 100, then it would be constant. Yes, exactly. That gives a good point. Let's say n was, for example, just because this is a nice, easy thing to cover. Let's say it was n divided by 2 right here. Well, whenever you have a linear or like n divided by 2 is still infinite. It's still infinity. You know what I mean? Like, okay, let's just, sometimes people, there's two methods you can go through this. You can replace infinity with n, or like you can replace n with infinity. So this while loop is instead while I is greater than or equal to infinity over 2, for example. Another example. In terms of this concept, you would still consider it to be infinity. Like this value is the same as writing just infinity in that section. So whenever you have, like, even if you do n plus 1, it doesn't matter. Infinity is still infinity. So this would still be the same complexity, which is O of log squared n. Is that good?
Okay.
Yeah.
So like, for instance, when I is less than or equals to infinity over 2, I is equals to 2 times I?
2 times I?
Yeah.
Okay, so then you have, okay, that's actually a good concept. I'll just write it here. While I times 2 greater than or equal to infinity divided by 2, and then you still have the I times 2 here. Okay, well, you will get to this when you take like the second year course, but you're incrementing exponentially I times 2, right? Actually, okay, I times 2, I times 2. I think this would be just O log base 4 of n, most likely. Because you won't need to pay attention to the bases of your logarithms. That is your second year or your next course that you will take, which is algorithms 1. But it would still be O of log n. Yeah. It would just be like faster. Okay. Just so it doesn't confuse anybody later. Perfect. Okay, we're going to continue on. Okay, I'm going to go through the next couple faster because they're relatively simple. It's what we covered before. We're iterating through from 0 all the way to n in this part. And then in the second part, we're also iterating through 0 to n. This sum, like they put a lot of random stuff just to trick you. We're not incrementing by anything we iterate by, right? It's just the sum is equal to I plus j. Sum does not affect the loop. Therefore, we can just ignore it. So this would be, let me just find my mouse, ignore. So this would be actually just O of n, which is from the first loop, times O of n, which is from the second loop, which is equal to O of n squared. Perfect. Moving on. Okay. You might look at this question and be like, oh, I don't know this. It has arrays, weird stuff. But trust me, just focus on the loops and you will understand it. Okay, we're incrementing with I. I starts at 1. And it goes all the way to n. And if you notice here, we're multiplying 2 by n for every stage. So it's I times 2. Therefore, we know that this initial loop is going to be O of log n, just at the start. This number can change as we go further down the loop, or as we go further down the codes. So now we have the second loop. We see that we have a value j, and we start at 0, and we go all the way to n. And we linearly increase j, so it's just j plus plus. Okay, we know that this second loop is O of n, because we go from 0 to 1, and you're just going 1, 2, 3, 4, 5. So you're going n times. And then this array stuff does not actually affect the loop. Does not affect loop. Therefore, we can just ignore it. So since these two lines are embedded within each other, we do O of log n times O of n, and this whole function is equal to O of n log n. Okay. I have like a small bonus and then some more page, so I can probably write some more questions, but I'll just do it here since it popped up. Let's say you had an example that had a for loop that went from O to n, and then you had another for loop that also went from O to n. And these two for loops were not within each other. What would the complexity be? Anybody want to take a guess? Yeah? Yeah, exactly. So sometimes he can trick you. Sometimes he can make multiple functions. Some are embedded within each other, some are not. You have to take the worst complexity. So if you have like a big group, like let's say, actually, yeah, I'll just keep this here. For example, let's say you have these two functions in one line. Imagine they give you this code block and he asks, what is the worst time complexity? Well, you see that here it's, here, let me actually write with like a purple. You see here, we found that this first code block is O log n, and this second code block is n log n. Well, what's worse out of O log n and n log n? Well, it's O n log n. So therefore, you can claim that if you had these two code blocks in one line, its worst case complexity would be O n log n. So he might ask you like he might not ask you like one function. He might ask you multiple loops. You calculate the complexity of each loop, and then you determine which is the worst, and you say that is your worst time complexity for the whole program. Okay. So now this is a bonus. This is something that was in an example of my upper year class that I'm currently taking. If you guys get this question right, then you're perfectly fine for the exam. I'll give you a second to actually try it while I take a drink of water. Okay. Does anybody have like an answer? No? Okay, I'll go through it. It is a little difficult, but once you cover it, it's actually relatively simple. You have one loop, which goes from 2 all the way to n. So we know that just at a first glance that this is O log n, because we don't know what it's incrementing by. We can assume that it's I plus 1, let's just say. And then you have a second for loop, which we start at j, and we go all the way to n. We go from 0 to n. And you can also just assume that this is O n, just for now. And then you're just printing I and j. And then you see here, okay, there's something weird going on. And since this is applied to something that we're iterating through, we actually have to look at what it's doing. So let me get my yellow out. Sorry, I can't see whenever there's a yellow pen. You see, it's applying to something we're iterating through. So now we have to actually focus our attention on it and see like, okay, what is this code? So we're doing j plus n divided by 4. Well, 4 or floored. If you had, for example, we have infinity, right? We can't really quantify infinity, but I'm just going to try. Let's say infinity is this pi. It's just a square. And let's say we divide the square by 4 halves. Well, from j, we're adding half of infinity. And if we have, like, this is infinity, this is a whole, this is n. If every single time we add to j half of infinity, 1, 2, 3, 4, this inner loop will only go 4 times. So it's something that you like think about. You can't just take the question at first glance and be like, okay, it's n squared, I have this. You should think about every single line and what is applied to what you're iterating through. So you have it here. This loop will only go, will only take 4 passes. So really, instead of O of n, oh, sorry, let me get instead of O of n, it's going to be O of 1. So this function actually takes O of n. Now, does anybody have any questions relating to any of these topics? Am I going too fast or am I covering enough?
Sorry.
Yeah.
So like, I thought it's going to be like O log n, right?
Mhm.
Because it's O log n base 4. Since it's
So for your questions, most likely in your exam, you're not going to have something as difficult as this because this actually you have to think about how the code is passing. Usually for your questions, I think at max, you might get n log n. You won't have like this simply, but let's say it was a different number. Let's say it's j plus j divided by 4, for example. Or let's say it's just j divided by 4. Then you're right. It would be n log n. Because the first loop is n, and the second loop would be, in that case, log of n. But for this case, since we're doing n divided by 4, we're taking 4/4 of a pi, and we'd reach the whole in 4 passes. Does that make sense? If you don't understand this, it's perfectly fine. This is like one of the most difficult questions that is in this example, yeah?
What if you have a nested loop and the inner loop has like something to do with the outer loop? For example, in this one,
Mhm.
you have j equals to I something.
Okay.
What else would you need to consider?
Let's say j is equal to I something. Okay, I think we will cover an example similar to that. Most likely, your example on your test or your final will not be too difficult. It's gonna be mostly what we've seen before, maybe a little bit more application. But I'll let you know when we go further down. Yeah, another question?
And do you know if we're gonna have to prove like big O?
No. I'm pretty sure from what Kareem has told me, what I've seen, you will not be able to prove big O. Yeah?
Could you do a question with like using use of a table? Like,
Yeah, for sure. I think the one coming up will use a table. Most likely on your exam, he won't ask you to prove its complexity. He might just ask you just list it. So I will go through a table just so you guys can see, but it will not be necessary for your final. Okay. Now we have an application question. Find the complexity of an algorithm that determines a patient between 100 normal people using big O notation. So I'll give you a second to think. Okay, we have the exact number. Whenever you see a problem and it doesn't say between n number of patients, between blah, 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 1,000, 1 million, or like infinity, if this number is ever n, then it would take on because we don't know how long it would take. He's just asking you like, okay, you have 100 patients lined up. How long would it take you to find out who is sick? Well, you would go to each patient and you would ask them, are you sick? Okay, no. Are you sick? Are you no? Okay. And that would only take 100 iterations. So in really, like, if you're going to write it properly, it's O of 100, which is also O of constant, which we write as O as 1. Does that make sense? He will ask you application questions like that. And you will also involve maybe some data structures. I will cover more examples later that are related to this, and I'll also verbally speak about some questions that might happen. But know that if he might ask you a question like this, you should kind of know how to solve it. He might ask, okay, what is the best data structure to solve this question, right? So yeah, take what I'm doing right now and take it as an example and go deeper within your notes, try and solve some more questions relating to this. Okay, I think this is one of the last, oh no, there's 2 more code things that we go through. Okay, this is the same thing that we covered before. We have I is equal to n divided by 2. And we're going all the way to n. Perfect. Now we have a second for loop. This has j. J starts at 2, and we're going all the way to n, but it's j times 2. Whenever you see this, you know that this inner loop is O of log n. Okay, now let's focus on the outer loop. I know I said before that whenever it's n divided by 2, you just ignore that and you write n. Well, that only works if it's applied here within your for loop. If it's here, you would still consider it as n divided by 2. Why do I say this? Is because if you write it as n, you're like, okay, you know, Joey said that this is going to be n, considered as n, I'm going to write it n. Well, then you would think like, okay, I does not pass through this loop even once. No. This, like whenever it's applied here, let's say this is n divided by 2, you would still consider it as n. But when I is equal to n divided by 2, you would consider that I is now a half of infinity. Well, you're working with infinities here. So you have half an infinity going to infinity. You're still going to take a half of infinity, which is infinity. I know it's a lot of infinities, but trust me that this is O of n. Does anybody like not understand that bit? I is half of infinity. You're still going to take an infinity to reach like the whole of infinity. It's kind of complicated. Here, let me try to write this out. You have I equals half of infinity. Since I is half of n, you know that it will pass through the loop. Let me just write that. You know it will pass through the loop at least a couple times. but, and then you're going all the way to the whole of infinity. So it would still take infinite times. Yeah, question?
If it was J is less than equal to n over two, then would it change?
Yes.
O log n?
Yes, exactly. It would still be O of log n, but it'd have a better base.
Okay, so big O is affected when like an operation is applied to n that affects n specifically, not the very.
Yeah, exactly. If it affects n specifically, then it will affect the big O. If it affects what it's iterating through, it honestly depends. But if you're going from infinity to something, it would still take infinity times. Okay, that was like a second complicated question, but it's okay. I had a lot of space there. The person who asked a question before, I'll cover it in the second space, but I think this is the one that you were talking about of how you should take in the graph. I'm gonna give you two ways to do this. One that takes a table, and that is like, in my opinion, overtly complicated, and one that just takes common, like, you just have to really see it, okay? You have this first loop. Fuck, sorry, I didn't know if I'm allowed to swear. I'd assume yes, because this is university, but, okay. So you have a first for loop. And you could just take it as this, okay, we're going from 0 all the way to n minus 1. Perfect. And now you have a second for loop. And you're going from, well, k is equal to j plus 1. So when it's 1, it's going to be 1, 2, blah, blah, blah. And you're all going all the way to n. So in this case, you would take like a geometric series and you would consider that, okay, we have n times n divided by 2, 1 divided by 2. In this case, it would be O of n squared. Now, I know I jumped right to this geometric series, but another easy way to do it is to just see like, okay, let's just say this was O of n minus 1 and then O of n. Well, this O of n minus 1 is a constant, let's just say. Well, it's just minus 1 of infinity, which is still infinity, so that's still O of n. And then this is also O of n. You multiply these together, and you have O of n squared. Now, in terms of getting like the more specific solution, you would use a table. So you have I. That's going to be an I. And you have I that's going from 1 or 0, 1, 2, 3, 4. And then you have J. J is going, it's incrementing 1 off of Y, which is 1, 2, 3, 4, 5. And you're going all the way to, in this case, n minus 1, and in that case, n. When you're doing this, you have to still consider that, okay, even though J follows I, it's gonna still be following I n times. So therefore, this inner loop is still O of n. Well, it's O from, yeah, it's O of n. And this one, even though it's n minus 1, it's still technically O of n. The in-depth table solution is in your notes, but it forms a geometric series. This stuff, like, I know you might think like, okay, I want to in-depth solve a geometric series, do all that, truly understand the problem. But to simply say it, if you see 2 for loops and each one is going by n, then it's just n squared. I do have the table solution, which I will post to the notes later. I just don't want to write it all out. Yeah.
I was gonna say, for the for loop of like, let's say if it was like n minus like 3 or n plus 1, it would still be O of n because it's following n linearly.
Exactly.
And it would only like be like exponential if it was either divided or multiplied.
Yeah. Okay, that's actually good. If anything here was like, okay, we multiply times 2, then that would be an exponential function. But you're right. Always, like, your life will be infinitely easier if you think of it in terms of linear functions applied to what you're iterating through, or exponential. Like, in terms of like the most complicated examples that you guys will have on your final, this is kind of what you need to know. Like in this case, even if you don't know all the theory of why it's O of n times n minus 1 over 2, you would still get it right because you just see like, okay, first for loop 1 or 0 to n minus 1 infinity. Second for loop j to n infinity. Perfect. Okay, now we're done with Big O. I hope I covered all your questions relating to it. But Big O is like a small portion of what your midterm is going to be on, even though it's probably the most important thing you cover. But yeah, going forth. Okay, we're going to start covering through trees. This right there, the pre-order, in order, post order, that's just so I remember it. It's a good example for you. So we know, for example, I'll just iterate through. The only thing that really changes throughout them is where C is at. And in terms of code, C just prints the value of the node that it's currently on. So I'll touch on like the code section of this and also like how you would do it through a graph, how you would find the pre-order, in order, post order of the graph. Okay, but you see here, I just have left and right. Depending on where C goes, it changes where you print the node, which actually changes the order that it's printed out on like the terminal. In terms of this section, I'll cover throughout everything, but the first question talks about building a tree. You have pre-order and you have in order. For pre-order, you have exam, fun. Wow. It's almost like you couldn't get any more obvious that it will be probably on your exam. And then for in order, you have MAFXUEN. Now, I'm probably going to go through this more fluidly because I have a sense of what's happening. But you see pre-order. This is where the order kind of matters. And this is probably one of the first things you should write on your exam, just in case you forget. Maybe you memorized it. If so, good for you. You have CLR. That means you go to the center, then the left, then the right. And then for in order, you have left, center, right. You have left, center, right. This is very important because in pre-order, it kind of tells you what the root node will be. Since pre-order starts from center, left, right, every time you have a graph, you will always read the center first, which means you would always read the root node first. So in our first example, we have to start with E as the root node. Okay, so we know that this is root. And now we can go in order and we can see what's next to this root node. Since in order is left, center, right, whatever falls to the right of E is going to be its right node. So we go to the in order values. We see, okay, this is where our E is. To the right of E is N. So we know that N is going to be to the right. Okay, and then we go back to pre-order. We see that, okay, X is the next center node. But you see, pre-order goes from center left. So X is going to be X is going to be towards the left of E. And then you go back to the in order. You see like, okay, you find X. Oh, to the right of X is going to be U. You write U. You keep going. You see, okay, now we're at A. A is going to be towards the left of X. Okay, to the right of A is going to be F. Okay, you keep going back to the pre-order. You have now M, which is going to be towards the left of A. Okay, you see here, we're now at M, and you can see like we've ended it. I think we've written all the functions. We have, and then we have F, A, X, F, U, N. Okay, M, E, perfect. You will have enough time during your exam to check through it. And I'll quickly iterate through the check. Was that like clear for everybody? Yeah? Yeah, for sure. So first thing you start with is pre-order. You know that since pre-order is center, left, right, you will, it's good, okay. Since pre-order is center, left, right, you know that the first letter in pre-order is gonna be the root node. That's what you start with. So you start with E. Okay, then you go to whatever is left. Most likely, they will probably give you maybe pre-order and post-order, you just have to look at kind of the order of where the center follows. But in this case, they give you pre-order and in order. Most likely it's going to be the same on your final, but you have pre-order, you have in order. Okay, you know that in order, you have the center and then you have the right. So whatever comes after the center is going to be your right node. So right here, you know that N will be your right node because it's to the right of E. So after you read E, then you read N. And if you follow through it, like in order, let's say you're going from the left, you're now at E. After you read the center node at E, you go to the left of E. And in that case, like it comes more clear when I go through like each. So I'm gonna do that actually. So pre-order. This is just for a test. Should move it right here. I'll also make it known that I can hear every conversation from like my spot here. So just try to be mindful of that. It's a little distracting. Okay. So just, you can test this easily. Like if you're stuck on the exam, you will have enough time. Don't think that, okay, you're going to be pressed for time. You will be fine. You have pre-order. Okay, let's see the pre-order. Pre-order is center, left, right. So the first thing you do is you read out the center, which is E. Okay, now you travel left. You read out X. Oh, wait, no, you travel X. Okay, yeah. Travel left. Then you go to the center of left. Wait, yeah. And then you read out X. Then you go to the left. You read out A. You go to the left. Read out M. And then you go up. You see. Okay, now this is like the iterative step. You're going through the recursive call stack. Go back to A, and then you go left or right, which is M. And then you go up again. And then you go left, which is, right, sorry. Q, and then go up. I'm gonna explain this more clearly. Let me just write this down for now. And then you go down there. It's EM. Okay, in terms of navigating through like the code of like pre-order, post-order, all that, it's much easier if you think of it in terms of like its code. I know you think code and it's like, oh my God, this is gonna be more difficult than just knowing left, center, right. But trust me, like it helps. So in pre-order, you're gonna have, I'm just gonna call it pre, okay? You're gonna have a call towards the left. So you're gonna say node or pre-order, center left. So you're gonna be, okay, since it starts with center, center is always your print. So you're gonna say print. Then the next call is pre, node, going to left. Then the next call is pre, node, going to the right. Okay, in terms of this, the first node you have, you're gonna print right away. So that's why you print E first. Okay, then what's the next line in this piece of code? You're gonna push the node to the left, which you do. When you recall this function, you're gonna start back at the very top. That's why you print X. Okay, after you print X, you're gonna go back down here. You're gonna call the function again, pre. Pre sends a node towards the left. Therefore, from X, we're going towards the left, which is A. Okay, after we do that call, the function restarts itself. It's a recursive call back towards the beginning. Therefore, we have print. So we print out A. And then it's going to call towards the left. Right there. It's going to go down here, go back there. And then we're going to go back towards the start of the function. And we're going to print out M. And then we have these recursive calls that will now be returned, right? Or like exited through. So the next stop on M, after it is returned, it's going to go back to the top. Like right now, it's like visually going back to the top, but we have that call that's previously there on the stack. And the next step is going towards the right. So we start at A and we're going towards the right. Okay, we know that it's F. And now we have the next call in the stack, which has X as like its node. And then we go to the right, which is its next line. And then we print out U. And then we have E, and then we print out N. There's many different ways to actually learn how to navigate through a tree in order, per order, post order. I like looking at the code and also just knowing it visually. I know there's methods where you can draw sticks on each of the nodes, and that usually works too. But in this case, like it's better to have like a deeper understanding of the concepts, just in case if you're stuck, or if you have to write like a piece of code. I'm pretty sure Prim told you you did not have to write code, but during my exam, I did. Just putting that out there. Okay, so in pre-order, the check works out. And then I'm gonna quickly go to in order. In order is, so the print function just changes. It changes its order. So instead of printing at the start, you're gonna print at the end. So this is now very messy. So I'm just gonna write a smaller example. Boom, 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 boom. And then each of these nodes, just to relate it back up to the top in terms of its values. Okay, for in order, it's left, center, right. You're gonna go towards the left, towards the left, towards the left, and then you're gonna read out the center node. So this is why it's like recursive. You're gonna be printing from left all the way up to the stack. So now we print out the center node. In this case, let me go. In this case, you would be printing out M, then A, then you see, does A have like a right node? Yes, you would print that out, F, so you'd go here. Then we go back up to X. We see if X has a right node, then you go to U. Okay, now you go back up to E. You see if E has a right node, and it does, it's N. So in this case, if you check it, it does provide the right answer. Does everybody understand that iteration? I know it gets slow, but I'm covering everything just so you guys know it. You probably already know pre-order, in order, but just be patient. The harder stuff does come after this. Does that, you guys understand pre-order, in order? Yeah?
Sorry, yeah,
Paul?
so like, I'm trying to understand how you initially created the whole tree.
Okay, perfect.
So, wait, so like, because I, like, the method I saw you use was like, you went to pre-order, then you went to another.
Yeah, exactly. So what you first want to look at is the pre-order, because pre-order, it's center, left, right. That means the first node that it encounters is going to be the center node. So you can always assume that the first letter in any pre-order line is going to be your center node. Okay, so that's how you know, like, okay, I'm not going to begin with F or U or N. I know that I'm going to start with E. Okay, after you start with E, you want to look at the next provided line. Maybe it's in order, maybe it's post order, it does not matter. Because the order should stay the same. If it's post order, you're just gonna have left, right, center. You're gonna know to the left of center is your right node, right? But in terms of this, we are provided in order. So you see center right there. We know that to the right of center, we're gonna have the right node. And then you just keep going through that way. So we have E. Let me just write this down. We have E. We start at E. Okay, we see that E is here. We know that the right node is going to be N because it's to the right of it. Okay, and then you go back, you have X. We know that to the right of X is going to be U because it's in the right of it in the in order. And you just keep going through that until you're done. And how do you know you're finished? You're at the end of the line. Like every value has been used. Most likely, and you can kind of notice this if you do more than one of these questions, you're always going to produce the same type of graph. It's always going to be a strip with just right nodes. Exactly. So if you know it this way, you will know it for every kind of solution. Yep.
When we were doing the three order, when we hit E and we looked at the right node, which is N, why did we look at the left?
Oh, we didn't. What?
Like you said, N is the right node of E.
Okay, sometimes I say it left when I mean right. It's just like my brain is like
No,
lagging.
why didn't we consider U?
Oh, why didn't we?
Yeah, as a left node of E.
Okay, for in order, you technically, okay, that's a good question. Usually you always want to just look towards the right. Because the left, okay, for in order, when you go towards the left, it's usually you're going down the strip, right? So it wouldn't make sense to look at the left node of E because like in pre-order, you can see the left node already, right? So you have center, which is E, and then you know that towards the left of it is going to be X because it comes next in that order, right? And pre-order, the print is always first. So it's much easier to just look at pre-order and be like, okay, it's E, then it's X, then it's A. Because you know the print order, like if you do the recursive call in your head, it only takes one line to iterate through to print. In terms of this, it's honestly dependent on where the print, which is center, is at, like in the line of code. But you're doing left, center, right. That means you're passing through all the left and then you're printing, which makes it a little bit more confusing. That's why I go like in this method. This is the easiest way to see this problem. If you overcomplicate it in your head, you're just gonna be confused during the exam. But if you go step by step, like when I first did it, you will have your solution, guaranteed. Can't say guaranteed because then you might sue me, but like, I'm serious. This is like pretty much just it. You will have time to check through your code. Okay, just a hint or like a piece of wise words, I guess. If you do this, if you follow my exact steps and you do the pre-order and the in order, and let's say your in order is wrong, you're probably doing in order wrong. Okay, just follow my steps and you'll be fine. Okay, I will be posting it. And it will be like on my Discord, and there will also be a YouTube video that will come out with my explanation. Okay. So now we have some more traversals. So this is good practice. Okay, I talked about the code and I'll give you some examples for every single line of code. Does the line of codes help you or confuse you? Good, okay. Honestly, if you think about it in terms of code, so simple. I'll also do it in terms of like just navigating through. I'll do it both ways. In terms of drawing the sticks on the nodes, I never learned that way, so I won't cover it. But you can find, that's what YouTube covers. You guys are here. I'll tell you like the easiest way in terms of like my opinion. If you want another easy way, YouTube is perfect for some examples. Which traversal should we do first? Anybody? What, in order? Okay, perfect. Okay, we have in order. In order is left, center, right. Okay, so in terms of this nifty graph, in order, in terms of code, let's just say, you have a node that you're going towards the left. Then you print. Then you have a node and you're navigating towards the right. And then you have this function, which is called in. These are recursive calls to in. And then of course, I don't have the preliminary like checks, like if this node is null, then you skip. I'm not writing code, this is just pseudocode, just pretend I added that in. Perfect. So at the very beginning, you have left, center, right. In terms of just navigating through the nodes, you start at the root node and you travel left. You see, okay, can I still travel left? Yes, you travel further left. Okay, you see, can you still travel left? Yes, you travel left. Okay, can you travel left? No. So what's the next thing you do? You're done with the left. Now you go to center. Okay, when you reach the center, you're always gonna write it down. So right now, there's no more left. So the next step is center. So your first thing is C. Okay, now you go up because there's nothing else for you to do at this node. Now we're at A. Is there a right? Because after C, there's right? So we do A. Okay, you go up. We write down X because center is when we print. Okay, is there a right towards X? because that's the next line. After center, we go right. Is there a right? Yes. So then we travel to the right. We have B. Is there a left to B? No. Then we write B. Is there a right to B? No. So then we travel back up. We go to Y. Is there a right? Okay, after we're at Y, we print because we're now at the center. Is there a left? We're done the left. So now it's just center, right. So now we cover the right. Is there a right to Y? Yes. We go towards the right. Okay. Is there a left to Z? Yes. We go towards the left. Is there a left to M? No. We write M. Is there a right to M? No. Okay. We go back up. Is there, and since we're going back up and Z is the center, we write down Z. Okay. Is there a right to Z? Because after you print, you always ask, is there a right? Yes. You go to M. Is there a left to M? No. You write M. N. And then that's it. In terms of, that's how you should come out this. You should always ask, like, okay, is there a left? No. Print. Is there a right? Yes. Go down. Is there a left? Like after you're done this right, if you have a right, you're going back all the way to the start to the left. And you're checking through. In terms of code, I'll cover this small section, probably in all the examples, just because it's a lot to think about in terms of recursion. But you're at Z, okay? Pretend you're at Z. You've already traveled. Okay, when you're at the node Z, is now Z. You're traveling left. Is there a left? Yes. If there's no left, then it just exits. Since there's a left, we travel left. So now the new node is towards M. Okay, we're doing a recursive call. So we're now at the back to the start of the program. Is there a left? No. Then we print M. So now we see here, M is now printed. Okay. And then after we print, we go to the right. Is there a right? No. Then we go back up because the next call in the stack is Z. Or it's, yeah, this is Z. Sorry, I did not mean to write M. This is Z. So we go to the call that is like, that called this function because now we've returned back to it. So now we have Z. Okay, Z stopped when it's left because Z called this. So once it's returned, we return back to the print. So the next thing that we print is Z. Okay, now we keep going. We printed Z. Since Z is now exiting the print, we check if there's a right. Yes. Right? Yes. We go from Z. So Z traveling towards N. Right? No, traveling towards N. And then we do the same checks. Does N have a left? No. We print N. Does N have a right? No, we exit the function. So that's kind of why, like, if you write the code or if you just know left, center, right, both examples work. Yeah. Does that make sense for in order? I only have one example for each. So if you're struggling on some, then please let me know. Okay. Okay, the next one, let's just do post order. Okay, let's just go in order. Pre-order, left, center, right, I'm pretty sure. That's why I said like this top up here is for me, left. Oh, okay, I got pre-order wrong. Okay, never mind. Let's just do post order. So I'm gonna give you guys like 5 minutes to do it yourself. This is still in order, sorry. Center, left, right. This is post. I'll give you 5 minutes to do it yourself, and then I'll actually call on somebody and make sure that they have it right. And then I'll compare my answer to yours. This should, by the way, on your final, this should take you 5 minutes, maybe less. Like in these questions, you save the most time. Yeah, also snack break, I guess. But please try this question on your own. Oh God, how long have I been doing this? An hour now? I still have a shit lot. I have a lot to cover. Fuck. It's okay. Hi.
After this.
Answering questions, most likely, yeah. Oh, true. I think I'm fine now, to be honest. But thank you. I should fill up my water.
Is it scary being covered?
No, it's not. I got used to it after the first 5 minutes. First 5 minutes, I'm sweating. Fuck yeah.
This is like the midterm review video, right? So it's just what you're going over.
Honestly, I'm going over that, and I'm also going over like some of the final questions.
Oh,
But
okay.
this stuff is like you should review it,
Yeah.
because most likely there's gonna be some questions related to that. There's gonna be some questions related to football.
But like but would you say the final is mostly like
Also, by the way, you
post-midterm
are
content?
recorded. Just so you guys know, because I'm still hooked up. But yeah,
Do you think that the final is mostly post-midterm content, right? It's not
yeah.
like
You're gonna have like maybe like one theory question on this. That's why I'm kind of going through it quickly. While trying to go through it quickly, you guys should know this, because low key, like, if you don't know this, you're kind of lost.
That's true.
Like, that's why I'm covering it. After we go through here, like you can see, like I'm gonna have some heaps next, and like
Oh,
it's gonna
good.
it's
Oh,
gonna
good. Oh,
get
good.
yeah, it's gonna get. That's why like when people ask questions, it's nice to ask questions. I just want to cover this so I can, because I have 11 slides more to do, and I'm on 5.
Is
And
the programming question you think likely to be recursive?
maybe I would say, like, if you guys do have a programming question, it's gonna be relatively simple. It's either graph or
Tree, yeah.
yeah.
Definitely tree. I was thinking tree. The graph coding I think would be more difficult.
Oh yeah,
Oh, I don't
of
know.
course.
That would be really bad.
Of course. Anyways, I give him 5 minutes. Okay, I should be fine.
Oh no, you're doing well. Is this like your tablet? Or
Yeah, that's mine.
Okay.
That's what I use whenever I do like any tutoring or whatever.
No, I know. Because I also have like the Wacom. And
By the way, the question we covered,
yeah.
Daddy showed it in the class. Remember the one? Like,
I was
holy
so
shit.
glad. No, I felt like a genius.
Yeah,
I was like, oh.
nice. And you have like the answers to words that
Yeah.
you know it now. Right?
Yeah.
Perfect.
That was perfect.
And like now I know it too. So I'm like, I did not review that shit before. Really. Okay. Now we can start settling down. Yeah, Paul? Sure. Yes, it does. No. Always, there's always gonna be in order, and then the next turn. Because pre-order always starts with second note. I mean, post order. Yeah, pre-order, it's probably just always gonna be there. Okay, now that you guys have settled, has somebody solved this? No? Okay, I'll give you like 5 more minutes. Oh, yeah? You wanna see or you want? Sure.
C A E X M N Z Y.
So I'm gonna write that down. So if you can say it one more time. C. Hamdi, what did you say?
C A E X M N Z Y.
Okay, now let's see if he's correct. Does anybody think he's correct? Wow, nice. Okay, so let's go. Okay, left, right, center. I think post order is the one thing I have the most trouble on, but let's see if I can get it. We go to the left, we continue. Is there a left node? Yes, we continue. There's a left node? Yes, continue. Left node? Yes, we continue. Okay, is there a right node? No. We print out C. Now we go back up. Is there a right node to A? No. Then we print out A. We go back up. Is there a right node to X? Yes. We travel to that right node. Is there a left node to B? No. Is there a right node to B? No. So then we print out B. Hamdi, you're looking really smart right now. Now we go back up. We have Y. Okay. Is there a right node to Y? Yes. We go here. Is there a left node to Z? Yes. Is there a left node to M? No. Is there a right node to M? Yes. So then we have M that we print out, or well, it's no, no and no. So then we print out M. Now we go back up to Z. Is there a right node? Or well, we already covered the left, so now we're at right. Is there a right node to Z? Yes. We go to N. Travel to N. Is there a left node to N? No. If there's a right node to N? No. So then you print out N, and then you travel back up, and you go to Z. And then you travel back up and you read the center and you go to Y. So when I was doing this exam, it didn't really help me at the time. But a nice trick is that post order, the arrow goes up. And for pre-order, the arrow goes down usually. Oh, I'm missing X. So we go here. Yeah, this is when I would print X. Okay. So you would basically see, okay, after you travel through a node towards the left, the questions you're asking is from here. Does it have a right node? No, you print. And then you keep asking those questions. So that's kind of it. In terms of code, it's relatively simple. You have post, which is a recursive function. You're going to send the node to the left all the way, and then you're going to ask post again. You're going to send the node to the right all the way. And then when the recursive function stack like collapses, you're going to print each of the nodes. So if there's no left, and if there's no right, you print whatever the node is. Does that make sense for a lot of people? I know everybody was confident with Tommy's answers. Good job. You got it right? Okay. I'm going to move on because after this, the next concept is really like, it's really important. So we did post order. Now we're going to do pre-order. Pre-order, we covered it before, center, left, right. I'm going to not cover the code for this because I've done this in the previous question, but I'm just going to go through it. So we have center, we read out Y. Then we have the next node, we travel to the left. We print out X, because after we go from the left, we recursively call back to the function, and then we print. Whenever you see C, think of it as print. Okay. Now we see, is there a left node? Yes, we travel to the left. Is there so after we travel to the left, we come back here. Okay, and we have C now, so we print, it's A. Then we see, is there a left node? Yes, we go towards the left. After we're done going towards the left, we go back to the center and we print it out, C. Okay, once we're done, we go back up the stack. Sorry. A does not have a right node. Done. So after we're done like this half, everything falls back. Every function's returned, and when the function is returned, it starts off where it left, which is this last recursive call towards the right. So does A have a right node? No. We continue because it exits. Does X have a right node? Yes. So we go towards the left. Does B have so once you go towards the left, once you go towards the right, sorry. After you're done this step, you're going towards the right, you start all the way back towards the end and you print out B right away. And then you ask, does B have a left node? No. Does B have a right node? No. So then that function cancels and that call cancels, and then we go back to Y. Now we're back towards the left. We're starting here. We're going to go and ask if it has a right. Y has a right? Yes. We go towards the right. We have Z. Okay. We print out Z. Because after you're done this call, you're going back to the print. Whenever you go to the right, just think you're printing. Now you go to the left. Does Z have a left node? Yes. You have M. You print M. Does M have a left node? No. Does M have a right node? No. You go back up to Z. Does Z have a right node? Yes. Then you print out N. And that is pretty much it. Does that clarify like this thing? You're probably gonna have like one question max, maybe on this topic, just make sure you understand the navigation. The first thing that I wrote on my exam was what pre-order is, what in order is, left, center, right, right, center, left. And that was pretty much it. Okay, now we're gonna cover heaps. I wrote a sheep here because I'm a sheeps. Get it? She heaps. Yeah. Bad joke. It's okay. But heaps are very important. These questions I'm covering have been like from your previous midterms. You gotta know this. So I'm covering it again. The questions might be very similar. Okay, so you have this one heap and it's a max heap, which is important because it depends on how we're gonna order it or sort through it. And you have the following operations: insert and remove max. You should kind of know what this is. Like if he doesn't provide you an explanation, you should kind of know like, okay, insert, you're gonna insert a node. You remove max, you're gonna remove the max. He provided that there because he's very nice. Okay, and you have the first question. Draw the max heap after you insert 11 to the original max heap. Okay, for these questions, you must write all your steps out because most likely the marks are gained and lost within this area. So I'm just gonna write down the original 3 and 4. Okay, so now we're gonna be adding, oh no, okay, the first question is draw the max heap after you remove max. Okay. So we're gonna be removing max. So after we remove 11, think of a max heap like a complete tree. It's always wanting to be a complete tree, right? So it would never have a node like this because in that case, it would be an incomplete tree. I'll cover that later, but that's just like a brief overview. So whenever you remove 11, you're gonna take from the leaves of the last, like, okay, let's say this is H. You're gonna take from the leaf from after H minus 1. So in terms of this, I'll just write it out. It's probably clearer than my example. So we have 5, 8, and we have 3, and then 4 is going to be actually inserted there. Why did we not take 3? If we took 3, it would not be a complete tree. So we take the lowest node and we bring it back to the start. Does that make sense? Because this part is probably the most important. The rest is relatively simple. Okay, so just to draw like an arrow so you guys kind of know the movement, we remove 11 and we insert 14 back into the root, or 4 back into the root. And then we see like, okay, this is not a max heap anymore because 4 is not the lowest number. So now we have to upheap, and we have to upheap until we have an actual max heap. Okay, what are the steps to this? Well, we compare 4 to 5 and we compare 4 to 8. 4 is less than 5, 4 is less than 8, but we can only switch one node. So which node should we choose to switch? Well, 4 is closer to 5 than it is to 8. So therefore we switch 4 with 5, sorry, right there, 4. This is now 5, this is now 4, this is 3. And then we have here, this is 8. Is this a max heap? No. 5 is less than 8. So we go through another iteration. We see, is 5 less than 4? No. That side is good now. Is 5 less than 8? Yes. So then you switch 8 with 5. As you're going through like with the 4 step, you would compare 4 to 3. Since I saw it was a min, there's no more changes. But yeah, that is it. Let me just, yeah.
I'm not confused. I don't know what I would do it this way. Usually I thought you were going to switch it initially with 8, so 4 just stays in the side.
I can write down that like example, but usually
Not a binary search.
no, it's a heap.
Yeah, so like they just switch 4 and 8. Yeah.
That's true. That's true. You could, but usually like in terms of what I was taught, you would switch it for the lowest and then you would up heap. You would want to keep, like in terms of heap, I know this is similar to like an AVL, but I would prefer it to be like greatest on one side, less on left. You could probably do both, but let's say this question is 3 points. Let's say like each of one of these are 3 points. They're probably wanting you to draw this 3 times. So I would ask, I'll write it down and ask the prof that question. Can you switch 4 with 8? Most likely you probably could, but from how I learned it, you would switch 4 with 5 and then 5 with 8. It also just looks nicer, so I don't know. That's a good question. Okay. Any other questions relating to this? No, there wouldn't be a difference really. Yeah.
Removing the max.
Mhm. Yes. After you remove the max, the root node would be the leftmost leaf. Exactly. Any other questions? Most likely during your final, you're not going to have an easy graph like this. This is just to give you an example of what steps you should take. I can't cover like a big example because I'll run out of time. But going forth, apply the same methods to a bigger example so you kind of get the clear sense. And a fun way to kind of test your learning is you take a big heap and you just keep removing the max until you're left with one node, right? That's how you truly understand, like, okay, I know how to do this. Okay, now we're gonna draw the max heap after you insert 14 into the original. Okay, so the same thing, we're trying to keep a complete tree in terms of maps. So we have 14, here, I'm just gonna write it to the side. 14, 5, 3, 4, and then 8. Where are we gonna add 14? Well, we're trying to keep it to be like a complete tree. So we're gonna add it to the left of 8. So 14. I tried to stress that this is the left. Let me actually just redraw it so people kind of know. They'll watch most likely, but if you're just covering the notes. We have 8, and then there. Okay, and then you take a step back. Is this the max heap? No. We're gonna go up heaping until it is a max heap. So now we have 14. We compare 14 with 8. 14 is greater than 8. So therefore we swap it. 3, 4, 14 now, and 8. Okay. And then see, is it a max heap? No. 11 is less than 14. So now you would also swap 11 with 14. 14, 11, 8. And then this left side stays the same. Using code, you would actually also check the left side, but since we know we're just adding 1 to the right of, or to the right of 14, we're good. Yes?
When we insert 14, why do we insert it to the left of 8?
Okay, that's a good question. In terms of a complete tree, I have an example here. I think it's next. Yeah, complete full. Okay. A complete tree is a perfect tree from height h minus 1, where it has 1 less leaf at h. So we're gonna always try to preserve a complete tree. So if you added it towards the right, it would actually not be a complete tree because we're trying to fill it in from left to right. That's why we added it to the left. So if you do add it to the right, it would be incorrect.
Okay, so it's just, we're just trying to follow the complete line.
Exactly.
It's just supposed to be as far left as possible.
Yeah.
Let's say there was a node to the left of C, then you have to insert it.
Okay. Let's say if you're here, just for example, this is great to cover, I guess. Let's say you have just a node here and it says, okay, you need to add 1. You'd actually add it right there. Add 2, keep going. You know what I mean? Add 3, it'd be to the left.
Oh, so if you add it to the
Yeah,
most far left.
exactly. Okay. Actually, I'll just, for example, but this is just your solution. Okay. So now we're gonna cover theory. Okay, this theory is not everything you need to know. It's the basics. I tried to cover everything, but it's too much. I am gonna post my notes that I took throughout the lecture or throughout when I took this course, probably on my Discord, and I might attach it to my lecture notes that I'm taking today. You guys should review these notes. I'll show you what they kind of look like now, if I can find it. Okay, this is not there. It's this one. Like, this is everything you need to know. And yeah, it's just basically everything you need to know in terms of theorem. I will cover a little bit today. So I do ask you to like pay close attention. But if you cannot see, like, these pages are covered and it's 4 and it has everything. So if you just go through this page once, you know all the theory. So I will post that and give that to you. Okay, so covering perfect, complete, and full trees. Guaranteed you might have a question. It might look something like, let's just say, it might look something like this, where you have a tree, you have nodes, look how pretty it is. And it might ask you, is this a complete tree? Is this a full tree? Is this a perfect tree? Well, let's just go through the definitions at first. Complete tree, it's a perfect tree from height h-1 with less than 1 leaf at h. So in terms of this, let's just see. Let's say that this is our tree. This is h, right? It's a perfect tree from h-1, h-1, and then we have at least one node at h, and it's always towards the left. That's just all you need to know. If it's towards the right, it's wrong. If it's towards the left, you're fine. It just fills it in. Pretend you have like a bucket and you're putting in water or a pail of sand. You're gonna fill the left to the right. How do you read left to right? So pretend you're like reading words instead of nodes. Just whatever you have to do to associate it to the left, that's just of utmost importance that you know this. Ingrain it into your mind. Okay. A full tree. Well, we used it in the above definition. It's a node that has at least or has 2 children. So this h-1 is also full from this because every node beyond that has at least 2 children. Okay, perfect. Think of it as full and complete. It's a full binary tree with all leaves at the same level. Okay. So something like this would not be perfect. Something like this would not be perfect. That's still not perfect. That's not perfect. And it's also not complete. And then this is perfect. So in terms of this example up here, does anyone want to take a guess? Is it full, complete, perfect? No? Okay. Well, let's just go through the definition. We know that this is not a full tree because it's missing. Is this okay, so if it's not a full tree, then it can't possibly be a perfect tree. So it's not perfect, not full. Because I don't know if you guys still remember discrete math, but this is how I associated it when I took it. If it's if perfect, then full. You know what I mean? Think of it like this. It has the same truth table. I remember it. Oof. True, 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 false, false, true, false, false. Oh my God, this is like taking me back to memory lane. False, false. True, true, this is true. True, false, that's false. True and true. So that's how you see. If it's not full, it cannot be perfect. Yeah. Don't look too closely into that. It's not mathematically proven. Just think not full, not perfect. And then is it complete? Exactly. Somebody shaking their head? No, it is not complete either. So it is none. Okay. Now let's say you're given like an example like this. Is it full? No. Is it complete?
Yeah.
Yes. Is it perfect? Well, if it's not full, it's not perfect. Okay. How if you're giving an example of a full tree? Is it full? Yes. Is it perfect? Yes. Is it complete? Yes. Okay. Now moving on. You got some formulas. I don't know if you guys covered formulas or if you forgot about it. I'm going to remind you because they're very important. These notes will be provided. So if you're writing it down, it's okay. I'll give you a couple minutes to do that. I made even like a key, like a map, you know, maps have keys on what each of the variables mean, because that's like the most confusing part of whenever formulas are presented. I'm like, okay, what does alpha mean? Anyways, I provided it all for you and I wrote it out neatly. I did this last night, so yeah. Okay, I means internal nodes, E means external nodes, N is the total number of nodes, and H is the height of a tree. Okay, do you guys, have any of you guys taken physics? Yeah, do you know like the physics sort of questions where you're provided with something that you don't necessarily need to solve the problem, but you have to use another formula to get what you need? That might occur, maybe, on your final. They might ask you something like this, and this is where the definitions kind of take in play. Were you guys, did you cover these formulas? You just forgot about them? Perfect. So there might be a question like, what is the number of internal nodes if you have a perfect tree with heights equal to, somebody give me an easy number. Anybody? That's a hard number, 3. I can't do, you're not gonna have a calculator. So like, it's gonna be relatively simple. Okay, what is the number of internal nodes if you have a perfect tree with height 3? Well, you might, oh, these are like the 2 things you write down, by the way, on your exam or your final. First thing you write down, pre-order, in order, blah, blah, blah. Or you can just write left, right, and then you know kind of where the center goes. Second thing you write down are these formulas, because God, you will forget, okay? So that is it. Honestly, if you see here, these 2 are the same. This one you don't necessarily need, but it is very useful. Yeah, and then the rest are just like, you have one which just follows from each other. You just use some basic algebra. And then you have 3, which you kind of have to know. I kind of starred one because it's very important. So should I give you guys 5 minutes to solve this? You can see you're given height of a tree. You look at your formula sheet. There's nothing to do with the height of a tree. Are you stuck? Well, no. You check, okay, you read the question. It's a perfect tree. We know that if it's perfect, then it must be full. So we can equate it to that. If it's perfect, then it must be full. Okay, well, we have a perfect tree formula that takes heights. So we know we must use it. I'm going to use just a different color. We have n is equal to 2h plus 1 minus 1. Okay, so now we get the total number of nodes. Well, total number of nodes is equal to 2 to the power of 4 minus 1. I think 2 to the power of 4 is 16. Right? 2 times 2, 4 times 2, it is 16. Oh my God, I'm so good. Okay, minus 1, that's 15. Okay, we have the total number of nodes now. Well, do we have a formula that can solve for something? We know we don't have I, and we don't have E. So we can't use these 2 formulas, but we can use this one. Okay, so we solve for it. If we find external nodes, you can find internal nodes. So now you just have to solve for external nodes. Well, you have 15, I have to just write the formula here. Plus 1. Well, you have now 15 is equal to 2e plus 1. 14 is equal to 2e. You know, e is now equal to 7. So now you have external nodes. You have total nodes. Well, you know that okay, we have e is equal to I plus 1. We've taken it from here. Well, if you do some quick algebra, you have e minus 1 is equal to I. So now we know that internal nodes is equal to 6. So that is kind of it. That's why I said like, oh my God, this is like a physics question. They don't give you what you need, but they give you something to solve for it. Yeah.
Why couldn't you use I is equal to n minus 1 divided by 2?
You could. I think I just did not see that. But like, that's what I'm saying. Like, if you don't write down all of your formulas, if you only know those two,
It won't
you'll be
use the
fine.
answer though.
It won't give you the same.
They use 7, no? I think you flipped E and I.
Oh. In I.
So E is equal to 7, that should be I.
Oh, yeah.
And then that would be,
I would be 8.
oh, sorry,
Hmm.
yeah, so you're on E equals 7.
Yeah.
It should be I. Internal.
Let me check my notes. So I did write this quickly last night. I'll talk to the professor about this and get like the correct formulas. Maybe unknowns internal. Yeah, because in terms of my book, it's correct. Yeah, I'll talk to the professor and see if I can get like confirmed, or you can quickly look in your lecture notes. But I will do that check. And you could also like verify that he might give you a bigger number and you can't verify it this way, but you have a perfect tree. You have a height that's 3. I think that's 1, 2, 3. Well, you have 1, 2, 3, 4, 5, 6, 7 external nodes. And how many internal nodes? Okay. Yeah, I'll probably check with the professor because I think I might have messed up. That's okay.
The height is by the edges.
Oh. So it's like 0, 1, 2?
0, 1, 2.
Thank you. Okay. Yeah, it's been a while since I done or like calculated the height, just to let you know that it's not used too much. Okay, that's 3, sorry. Okay, so it's 1, 2, 3, 4, 5, 6, 7. That's external. Yeah, and then internal would be 1, 2, 3.
External is just the children.
Yeah.
Oh, okay.
Just the bottom.
1, 2, 3, 4, 5, 6. Then it's correct.
No.
What? Okay.
Should be all the bottom ones.
Oh, all of them. This?
Yeah.
Oh, okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah. That is wrong. Okay, I will ask the prof for the formulas. The math is just relatively simple. Maybe I copied it in my notes wrong because I only took it from my notes. I didn't really look at the slides. But you will have like maybe a problem like this, probably relating to something I starred up there. So please note that down. I will give you the corrections later. The professor will hop in sometime soon and I'll ask him all the notes that I put at the end. That's what I just solved. Okay, so now you have the second important slide. Using the numbers, create a BAST, min heap, max heap, and AVL tree. And I will have a 2-4 tree question coming next. Now, you have these numbers in this order. The professor told me that you guys kind of messed up a little bit with max heap and min heap and BST in terms of how you wrote it, but hopefully I can like come at that.
The mistake in your equation is n equals to e minus 1. Then you go plus 1.
Oh, okay. N is equal to 2e. Yeah, that's probably it. Where is my thing? N is equal to 2e minus 1. Let me just check one last time. Because maybe I was like reading it at night very fast. Oh, let's see. Yeah, it is -1. Okay, well, don't write notes at 12. Okay, so in terms of this, you would just, do we use it? Yeah, it would be 6 now here. 6, because this is -1, -1. And then you have 6, 6 -1, so E is now 6. So now it is 5. Thank you so much. Okay, perfect.
No, it will be like 15 plus, yeah, and then 16 divided by 2 is 8.
Sorry,
So it will be 15 plus 1.
15 plus 1,
For the
okay.
two- Yeah, for the external node, 15 plus 1 divided by 2, that's 8, not 6.
Oh, so this is +1 then?
You know when you like in math, when you put a subtraction.
Oh.
on the side, it's plus.
Oh, yeah. Never mind. Okay, God, sorry. There we go. So it's 6 plus 1 is now equal to 7. So I is equal to 7. Yeah, perfect. Thank you for the corrections. Okay. So now moving on. Oh, because you changed it to minus. Yes, you're right. Oh, wait. Okay, give me a second. Okay, give me a second. This is just, this is E equals I plus 1. This is N is equal to 2E minus 1, right? That was the thing in my notes. Yeah, okay, sorry about that. So now you have N minus 1 or N plus 1 is equal to 2E. We know that N is equal to, and in this case is 4. No, it's 3. So 3 plus 1. No. Oh, yeah. Okay, in this case, N is 15. Yeah, you're right. 15, 16, 16, 16 divided by 2, it's 8. So E is equal to 8. Okay, and if E is equal to 8, we have E is equal to I plus 1. 8 is equal to I plus 1. So we know that I is equal to 7. And I think that is correct. Perfect. I will probably write this neater, maybe near the end, but I still have a lot to cover, so I will try to speed it up. I don't know how long we have the room booked too, but okay, perfect. So we have the numbers in this order. We're gonna create a BST at first, yeah?
Could you go over the corrected formulas?
Yeah, for sure. Okay. The only change is right here. Sorry. The only change is right here. Instead of E plus 1, it's E minus, or it's 2E minus 1 instead of 2E plus 1. Yeah?
Does the root count as
Does root count as what? Sorry?
internal mode?
Honestly, I do not know. I don't think so. It does count it as internal? Okay, then it does.
So it says like it has to have like
Mhm.
two sub trees or two sub.
Oh,
Yeah,
okay.
two
Okay.
sub-type.
I will get more clarification from the prof. In terms of like actual theory, I did not review too much. I mostly reviewed the concepts and how you do them. And I'm just like telling you like, okay, you take these concepts, as long as you know, like in terms of application, what you're doing, you have enough to get a 50. If you want higher than a 50, which all of you guys should probably want higher than a 50, take these concepts and learn why it is so. Like, okay, what data structure creates a heap? You know, what data structure creates an ABL tree? That's types of questions that you should know. What is the complexity, or like, what is, actually, I will cover that question later, so I won't spoil it, but yeah, I'll cover it later. Okay, Moving on. You have numbers in this order, 5, 2, 6, 8, 15, 1. You're gonna create a BST. Okay, well, you have 5. Since that's all you have, you're gonna start with 5. BST, left is less, the right is greater. We're gonna add 2. 2 goes to the left of 5. Okay, now you have 6. 6, since it's greater than 5, is gonna go to the right. Okay, next thing in line, 8. 8. 8 is greater than 5, it's greater than 6, therefore it's also towards the left. 15, or right, sorry. 15. 15 is greater than 5, greater than 6, greater than 8. So then it's also going to be towards the right. And now you have 1. Well, 1 is less than 5. It's also less than 2, so it's here. Let's add like a couple more numbers just in case. Let's add 7. Okay, sorry? Yeah?
I just have a question. For the BST data structure,
Mhm.
is it like similar to the AVL? Like, could you just explain the difference?
Yeah, AVL and BST they're similar in terms of like you're keeping to the left and right. AVL tree, I'm pretty sure you can have like, let me see, tough combinations. Ask me when I cover AVL. Like bring up that question again when I cover AVL, because it's like to the forefront of my mind probably.
And so for BST, it's just what the left nodes are less than.
Yes.
The right nodes are greater.
Exactly. Pretty much all you need to know. So if you add 7 to this tree, well, it's greater than 5, greater than 6, but it's less than 8. So we're gonna go to left and add 7. Let's say you added 2, or no, 3. Well, 3 is less than 5, but it's greater than 2. So if you're searching for something in a BST, well, how many steps does it take to search for 7? Well, 7 is greater than 5, and it's greater than 6. And then you look, 8. So if it's not to the left of 8, then you don't actually have it in the BST. Yeah, perfect. Any questions on that? Okay, similar question might come up. Let's say he gave you a tree, or like he gave you a list, and it was like 5, 6, 8, 15. Don't start in the middle. Don't like just pretend like, okay, I'm gonna make the most balanced BST. Sometimes it's just not balanced. Okay, you will encounter methods of how to like order your numbers so it is balanced, but don't start in the middle, start at the start. So it's okay if you have something at the end of the day that looks like this. You know, it's still correct. Okay, moving on. We have min heap. We kind of went through min heap before. You have 5. Okay, you're adding 2. Well, is this a min heap? No. Therefore, you have to up heap. 5 or 2 is greater than, or 2 is less than 5. So you're going to switch 2 and 5. Okay, now you have the next thing in the line, which is 6. You add 6. See, I'm like keeping a perfect tree every step that I'm adding a value. Okay, is this still a min heap? Yes. You continue. You have 2, you have 5, and you have 6. Now you're adding 7 or 8. It goes here. Is this still a min heap? Yes. You continue. 2, 5, 6, 8. And you're adding 15. Is it still a min heap? Yes. You keep going. He wants to see all these steps, unless he told you otherwise. So if you can kind of tell how many steps he wants to see in terms of the weight of the question. So if it's 6 points, he wants to see every single step. Okay, don't skim out on that or skimp out on it. Okay, you see I'm adding 1 to the left of 6 is because I still want to keep that complete tree structure. So now, is this a min heap? No, exactly. So now we have to up heap. We compare 1 with 6. 1 is less than 6. So we switch that order. I'm going to do a square because I don't want to rewrite that side. It will take too much time. But we have 6 we have 1 in here, and now we have 6. Is 1 and then we keep going. Is 1 less than 2? No, so we have to switch them. So now we have 1, we have 2, and we have 6. And then this side, I'll just write it now. We have 8, 15. And now that is your min heap. See how many steps I show, like at each stage, I show like, okay, this is being compared, blah, blah, blah. That's what you kind of want. It's kind of what he wants to see. So now I'm gonna just continue. Now we have max heap. Max heap is very similar. Sorry. So I'll just quickly go through it. You have 5, you have 2. Okay, these are still balanced. You have 6. That's not balanced. You switch 6 with 5. Now you have 2. Keep going. You're adding 8. So if you have add 8, 8's going to come on this side. Okay, now you have to upheap again. Sorry. This is going to be switched here. You're going to have 2 switching places with 8. You keep going. You have 5. Okay, this is still not a max heap. Therefore, you switch 8 with 6. 5, and then 2. And now this is a max heap. So then you add the next value. You're going to be adding 15. Wow. So you have to do this again. You have to max heap and switch 15 with the places of 6, and then switch places with 8. So I'm just going to skip those 2 steps because I think you guys understand the process. We have 6, and we have 2, and then we have, sorry, we have 2 here, we have 6 here, and then we have 5. Perfect. So now this is a max heap. Now you're going to add 1. 1 goes here, and we're done. Does that make sense for everybody? The max heap in, yeah?
In both min and max,
Mm-hmm.
use uphill process.
Yes. Both min and max, you want to uphill, upheap. When you're adding, you upheap. When you're removing, you downheap. You replace it with the leftmost node, and then you downheap. Because you have to see, like, okay, is this supposed to be there? Or is it not? Okay, now we have AVL. In my mind, I distinguish between AVL and actual things by doing like a square. It's the same thing as a node. I just write it as a square because that like changes my focus. So we start the AVL with 5. Okay. Properties for AVL is that you always want to have the same height on like every node. You want to like balance it. So AVL, you know the balancing factor. If it's greater than 2, I think, or 3, you have to rebalance. I will know the second I finish this question, which is true. So you have, it's similar to the BST where the right side is less, left side is, or the left side is less, the right side is more. So you have 5 in the middle. Now you're adding 2. Okay, this is still balanced. Now you're adding 6. That is still balanced. Then you keep adding, you're adding 8 right here. Okay. Is this balanced? Well, you have 0 or 1, 2, 3, and then you have 2. The difference between that is only 1, so we're good. So now we add 15. Is this balanced now? Well, you have 4 and 2. The difference is 2. Now you have to rebalance. The professor will ask you specifically, label X, Y, and Z on both your rebalanced version and your balanced. Okay, so you must know this exact way of how he teaches it. In my head, this is X, this is Y, this is Z. Your professor prefers them backwards. He prefers this to be Z and this to be X. In my head, it's X, Y, and Z because it makes the most sense. Like it's in order, X, Y, and Z. But just note that whenever I write X, Y, and Z, switch them, okay? Because I can't do it mentally if I keep it the opposite order. Some key things to know, actually. You will encounter 3 things that might need rebalancing. You will encounter something like this. Okay, a tree like this that needs rebalancing, pretend it's a part of a bigger group. And something like this, where you have this node, you're going here, and you're going there. Okay, in terms of these cases, I'm gonna use some nice colored pencils or pens. This is a leaf, this is a leaf. This is also, this has 2 leaves. Boom, boom. This is a leaf. This is a leaf. Professor told me that you guys struggled on how to rebalance. Like you were just putting numbers wherever. Try not to do that. I'll show you like an easy way. So if this is X, Y, and Z, and if this is X, Y, and Z, okay. Let's see. We are reorganizing X, Y, and Z. Well, the Y always stays in the middle. We push Y up, and then we have X, which is on, since X, okay. X, okay, wait. Okay, X has to be on, give me a sec. X has to be on this side, I'm pretty sure, and then Y has to be that. Okay, let me just do another example, another way, I think. Right here. Okay. Perfect. So we have, yeah, that's the way I learned it. Either way, it works. You just have to like change your focus. Okay. Perfect. We have X, we have Y, we have Z. Okay. Now this works. Whenever you rebalance it, think like when you're rebalancing it with this structure, it is always going to have Y in the middle, X on the left, and Z on the right. And what happens to its note, like what happens to its leaves? Okay, let's see. We have, let's just start with the leaf on X. Well, this leaf, you know that it's greater than X. So it's going to be towards the left. Give me 1 second. Let me just pull this up from how I did it in the review, just to make sure. I think it's good. Just to make sure. There's like, it's shown like this online. That's the first copy. Maybe it's this. No, it's called rough. There we go. And this has not been saved. Perfect. Good. It's right here. Okay. You can see this is kind of how I ran through it with my friends. Okay, there we go. So you can kind of see here, we have X, Y, and Z. It's colored for you too. This node, since it's less than X, it's going to be always like towards the left of X because it is less. You can see right here, this green node, darker green node, is greater than X, but it's also less than Y. So as you can see, it's transitioned to being greater than X and less than Y. And then even for the blue ones, you can easily just kind of see like where it goes. And I'm gonna do like a little sneak and take a screenshot, paste it.
Joey, where does the ABC come in?
ABC?
Yeah, for the in order traversals.
Okay.
Isn't B supposed to be the top, not Y? Because Y should be like C.
I think you meant like for this, like in this example, you have Z, which would be at the top, and then you would have Z is less than that. Then you'd have Y, I'm pretty sure, and then X. I think you meant with that when it switches.
Like, sometimes like, see like you have to do, I remember the professor doing something like in order.
Yes.
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 And then like this example, it's X is A, B is Y, C is Z.
Mhm.
Another example could be like different.
Yeah, of course. Okay, so this is like okay, the professor, he taught me, okay, when he was teaching my class during the summer, he taught us first. He's never covered this before.
Okay.
But like he came up with new tricks, like the in order, pre-order, whatever. I did not learn it that way. I learned it by like just shapes. And also, I won't lie, the TAs were kind of yikes. So they also did not teach it like a proper way. This is just for your final. For your final, you're just expected to label X, Y, and Z. I do highly recommend you solve it in the order the professor gave you because it's very systematic in what you need to do. But in terms of this, like when you're rearranging this, sorry, you have 5. Your middle would be 8, left would be 6, then you have 15, which stays the same, and then 2. Okay, and now what you're adding 1. 1 goes on this side. Is that balanced? 1, 2, 3, 3. Yeah, it's balanced. So this is just the major rebalancing step. I'll cover another rebalancing. Like I was saying here, this is kind of how you have to think of it. You have to still consider like the leaf nodes whenever you're doing it. This third thing that I wrote on my exam after I wrote the equations for the graph and like the in order, pre-order stuff was these 2 examples. Because as long as you can replicate these 2 examples and you kind of know, okay, this leaf right here is greater than X. So it's going to be here. Okay. This leaf right here is less than, okay, it's between X and Y because it's greater than X, but it's less than Y. It's greater than Z, sorry, greater than Z, but it's less than X. So you know that it's going to be right here. Okay. And then Y. This node right here is less than Y. So we put it here. And we know that this node is between, sorry, I did that color before. Let me just find this. We know that this node right here is greater than Y, but less than Z. So then you would have it right there. So in terms of like actually just coloring it up, that's kind of what I did during that first run through. We had blue here. Every single example will follow one of these orders. So if you know like kind of how to do one of them, or like if you know these 2, you can figure out the rest. So like if you forget, just try to remember this example. These are the main 2. You can also switch them horizontally. So you can have something like a node here, and then a node here, then a node here. Well, it just follows similarly to this. Like I said before, X, Y, and Z are switched in your professor's notes. So follow the way his notes are written. Does that make sense from like anybody? I know it was kind of like jank in terms of how I covered it, but these labels and examples are, it's just kind of what you need to have like in your mind while you're covering it. Does anybody want me to go over it again or no? Okay, perfect. Because then we get to my favorite part, I think, sooner or later after this. Or we go PQs. Okay, now this is more things. So we're gonna delete, here, let me just grab this. We're gonna delete 11, assuming that the first step in the deletion operation selects 10 and to substitute the deleted 11. So like you were saying before, the professor taught you in order. The next line in order, you select to replace it. In terms of most of the questions that I've seen on the midterms, he actually specifically tells you what you should substitute the element with. So I think that was like mostly help for for assignments, but for finals, this is pretty simple. Okay, so we're gonna delete 11, and in place of 11, we're gonna substitute it with 10. So let's write that out. Let me see, can you guys see it when I do it like this? Or is that too small? That's too small. Okay, is that good enough? So I need to be able to, yeah, that's okay. Okay, so you have, let me see, okay, perfect. You have 9. I'm just gonna write this part as a square because it's gonna stay the same until it changes, and when it changes, I'll actually write it down. But you're replacing this with 10, And this goes still there to 13. And then you're gonna go to the left with 12. Okay. Is this balanced? Let's see. This is 1, 2, 3. Okay, this is 1, 2, 3, and 4. Did I count that? Did I count that right? 1, 2, 3, and 4. 1, 2, 3. I'm pretty sure that this is just not balanced. Let me cut it one more time. Okay, 0. This is like the proper way to count. 1, 2, 0, 1, 2, 3. 2 and 3 is balanced. Yeah, I think it is balanced. I think I did. I should skip a node.
You count it from the right subtree?
Yeah, here.
The right one, so from 9 to 11.
Oh. 9 to 11. Okay, 11 doesn't exist anymore. We're,
Yes, so back to 10.
oh yeah, yeah, okay.
So
1, 2, 3. Am I seeing this weird? 1, 2, 3, 4.
Usually there's two cases, oh, sorry.
Yeah.
Two cases, so you can use 10 and you can use 12. 10 usually corrects. You
Mhm.
don't use like.
They told us to replace it with the 10 in the question.
10? Okay.
Uh,
It should be alright.
I'm just gonna pretend that it's not balanced because I'm pretty sure that it is not. Oh God. I'm pretty sure that it is not balanced. When I did it last night, it was not balanced. I'm pretty sure. Let me just check quickly. Okay, I replaced it. Oh no. I think it was balanced.
Is it 10 not balanced? Yeah. And then
10 not
once-
balanced.
once balanced, and then the right side becomes like 9.
Okay, let me see. Just let me do that. 10 switches its spot with 11
Don't you count like the opposite direction, like the higher?
from up.
Yeah, no, like down to up instead of up to down when you're. trying to
Yeah.
do these.
Wouldn't it be the same? Because it would be 0, 1, 2, 3.
Oh.
And this would be 0, 1, 2, 2. It's the same. So I think it's balanced. I think I'm just gaslighting myself and thinking it's not, but like, yeah. Okay, I'm just gonna add another node. Fuck it. That's okay. I'm adding another node just so we can have like some practice.
I think it's not balanced because it's not those.
It's not. I know it cannot be.
Starting from the 10, you have 2 tries on the right side, but no tries on the left side. So it's 2 on the right and 0 on the
Yeah,
left.
so these are also two double nodes.
Oh yeah, yeah, you're right. You're right. Because it's 0, 1, 2, and then this is just 0. You're right. Thank you. Whoever say your name. Sorry? G? G? Okay. Thank you. Big thank you to G, guys. Everybody in the chat, give a like for G. Okay? Because he solved it. Okay. Smartest guy in the room. I'm sorry, everybody else. Okay. So we know it's not balanced in terms of 10 because this is 0. Yeah, this is 0, 1, and then this is just 0. Well, in here it's 0, 1, 2 for 10. And then this is just 0. So since we're switching it here, just focus on this. Okay, so now we have to rebalance it in terms of 10. Well, this is X, Y, and Z. So we know from before, whenever we have something like this, X, Y, and Z, it's gonna be flipped so that it's Y here, X, and Z. Actually, because Z is less than Y, and it's greater than between Y and X. So it'd be Z, Y, and then X. Yeah, because it's just the order that makes more sense. You see here, it's in the middle, so Z becomes the middle, whatever. So in this case, it's gonna be 9, Then we're gonna have 12, 13, and 10. And now we have like the rest of the function, which I'll actually draw out. 4, 6, 8, 7, and then we have 5 right here. 2, 3, 1. Okay, now is that balanced? Well, let's see. Now this is 0, 1. This is 0, 1, 2, 3. 1 and 3, there's a 2 difference. So it is not balanced. So now we have to label our XYZs. Keynote, XYZs in my head are backwards in terms of the professor. So just swap them. All you have to do is swap Z and X and Z. But this would be, so whenever we're balancing from the side that is greater. So the 4 would be considered our X. 6 is now our Y, and 8 is our Z. So in terms of this, if you draw it out, like in terms of just a small case, well, it's one of the things we covered before, X, Y, and Z. Well, Y is now in the middle. Then you have Z here, and you have X here. That's it. So now if you draw it out again, I'm lacking a little space, but I will draw it bigger and then also draw it out. So you might not be able to see the screen when I fully draw it. That's okay. You will have the notes. But you have, okay, when you're switching the order, you know that now 6 is going to be in the center because 6 is our Y value. You know that X is going to be down below. And with the example above that I gave you, you see here, X has its children on the right. So you know that whatever X is connected to, it's going to be on the right. So instead of X, that's actually a value that's supposed to be 4. This is 4. And then you have 2, 1, 3 that remain unchanged. Okay. On the right, or on the left, no, on the right, sorry, I was correct. You're going to have Z. Z in this case was 8. And then you're still going to have on that, the left of Z, which is 7. Or the right of Z, 7. And that would be it.
Where did you go back?
You're right. Yeah, you're right. You're right. You're right. It's right here. And why? Well, okay. We see in this example. So I actually drew the nodes out right here. So this is something like, okay, let me just draw this. Actually, I can just draw it out here. In terms of there, okay, we have 4, 6, and 8. And then we have these leave nodes. We don't really care what they are, just for the small example, just to illustrate what I've done. This is X, Y, and Z. When you put Y in the middle here, so this is now 6, you have 8 right here, and you have 4 right here. You know that towards the side it's going to be less. So 8, I mean, you know that towards the side is going to be greater. Wait, what the? Okay, I just mixed it up because I thought that it was like this, but it's actually towards the right. And even as I drew it here, I kind of messed up on drawing that. That's okay. But you're right, it does end up in the same spot. It's right here. So instead of this example, it's actually just one of these where you have this node and that node. And you know that the left node here is greater than this, but it's less than that. So it'd be in the middle. So it'd actually be right there in between. And it's in one of the examples above on the page. So if you see here, compare it to the red, right? The red's between Z and X. And that's it. Okay, does everybody kind of understand that? I know at the start it was a little rough. That's just the general concepts. Okay. Moving on. So now you have just a algorithm question. This is something that might occur on your final, so I'd pay attention. He might also ask you like, okay, what data structure does the ABL tree implement? What data structure does the BST implement? Yeah?
Show the final balance ABL tree.
Yeah, I can. Final balance ABL tree would be, I kind of drew it right here. Let me see. 6, 8, 1, 2, 3, 4, 1, 2. Oh yeah, okay, I have to, okay, so now I have to balance it in terms of,
But you're missing 5 as well. 5 should be the right.
okay, right here. Okay, yeah, that's kind of why, see, on Discord, I can just zoom out on the page and see everything. Okay. 5, let me see. Okay, so when we rebalance it again, we have X, Y, and Z, because this is the greater side. So we have X, Y, or, sorry, we have X, Y, and Z. There we go. So when we're rebalancing it, 6 is now going to be in the middle. I'm actually just going to zoom out so I can write it properly. You guys won't be able to see the question. Just know that I got this. Let me just quickly do this. We have, okay, so now this is just going to be 6 in the middle here. 6 right here. We're going to have 9. Okay, we're going to have 12, 13, then 8, then whatever is left of 9. Okay, this is going to be 8 right here. Then this is going to be 7. And then we have the rest, which is 4, which because 4 is Z. And then you have 5 right here. And then you have 2, 1, and 3. Okay, that is your final solution. And I will zoom in so you can see it. And I think that is it. So in the above example, let me just see, can I scroll, please? Yeah, it's right there. So your X would be 9, your Y would be 6, and your Z would be 4. And then you'd do the same thing in balancing. You'd put the Y in the middle, which is 6. On the right, you would put the Z, and then on the left, you'd put the X. That is it. Good?
Is your right node 4 or 9?
Right node?
Or 6?
6. The left node is 9. Let me just, right, I meant, sorry. Let me just, that's a 9.
Also, why are there 2 8s?
Is there 2 8s?
Left of 12, left of 9.
Actually, there is. Why is that? Okay, that's supposed to be a 10. I'm pretty sure. Yeah, that is a 10. Okay. Now this is done. Perfect. Okay, that is your complete answer. I'll probably write it neater, maybe if I have time. But yeah, so we have a 2 for 3 question next, which is actually really important. I did not have this question added before today, but somebody on Zoom was like, you should add it, so I did. But before that, we have a question about just the time complexity for searching. Okay, what is the worst case running time for searching for a key in an ABL tree? Anyone want to take a guess?
Okay.
Yeah, exactly. Okay, what's the worst case running time to search in a BST? Yeah, exactly. It's ON. Now you might want to think like, oh, it's also O log n because it's the height of the tree, but your BST can look like this. You know, sometimes you have a bad BST. So that's why it's ON. That was one of the trick questions on my final, I'm pretty sure. It was something similar. Okay, now you have a 2-4 tree. If you cannot tell, this is from one of you guys' assignments. I nabbed it from that. So if you got that assignment question wrong or you found it difficult, this will cover it. So from this 2-4 tree, we're gonna delete 90. Okay. So I have some like helpful tools. Every underflow can be solved using a series of fusions and at most one transfer. The underflow can propagate to the parent. So when you delete a node in a 2-4 tree, you will have an underflow because now you have one less node. It's not always the case that you have an underflow. Sometimes let's say you delete 15 here, you won't have an underflow, but in the other case you will. So now we have 30. Okay. Since we have an underflow, we're gonna take 75 and drop it down and combine it with 33. So this is what I'm saying, like we're gonna fuse 33 and 75. This is 75. Okay. And we're gonna propagate. So we have 10, 20, 22, and it's attached to the nodes. This is 25, 27. We're gonna propagate. We're gonna move 30 down into this spot and move 20 up. Okay. And while we're doing that transition, this would have only 2 nodes and it would have 4 leaves. You cannot have that happen in a 2-4 tree. So we're also gonna transfer these leaf nodes right there. So in terms of like how you would draw it, it would be 22, 30, 15, 27, 33, 75. And then this left side would just be 20 and 10. Then you'd have 21, which is here. Then you would have in the middle, you would have 13, 15, and then you'd have on the side 2, 5, and 7. That's like probably the most complicated. Overflows are easy because you just move up. Like if you add a node, you take from this middle, you push it up. Okay, so like in terms of this, let's say you had a 2-4 tree that's like 5, 8, 10, and then you had 11, or you had a full leaf, which is 11, 12, 13. In the middle here, you had like 2 and 3. Right here, you had in the middle there, you had like 6 and 7. And at the end, you had just 1. Let's say if you wanted to add 15, then this would also probably break because you would have to add 15 to the end. And that does not work. So you would move 15 to the middle. Okay. And then you'd have to like propagate it up. So if you move 15 here, so for example, in this case, it's 5, 8, 15 now, you would have to take the middle term and then move it up. So now this is 10, right? And then you'd have to like go further. I just put this one example. I wasn't gonna cover 2-4 trees because it's not like a main portion of your exam, but this is just so you know how to deal with underflow. Does that make sense? Yeah.
For the one on the left, we have taken 20 instead of 22.
Let me see. If you took 20, okay. Usually you always take the one that's further to the right. If you took 20, I'll tell you why. Because if you took 20, you would have to fuse this. Okay, if you took 20 here, this could still be pushed there. Yeah, it could still work. It could still work. But these two would have to fuse together instead. I'm pretty sure you just take the rightmost, usually in these things, you take 22, but it would still work technically. I don't know how many marks you would lose, but it would still work. So if you're used to like just taking 20, sure. My advice is like whenever you have 3 questions or like 3 10, 20, 22, okay, let's just call this 32 and 34. Whenever you have something like this, you always take the second to one and you bring it. Whenever you have something like just 3, 10, 20, and 34, you would take this one. It's kind of forming that pattern. You leave the greatest, but in terms of you only have 3, you take the greatest. Okay. Just going forward. Okay, now this is my favorite part. And I will have to zoom it out. I'm sorry if you cannot see. I think it's clear. We have Dijkstra's, Prim's, Kruskals. Do you guys know these graphs well enough? Good. Okay, perfect. And it's just I'm gonna cover it briefly. Do you know BST DFS? Perfect. That's why I left them here. This is graph first search. That means you navigate through all nodes and then you move down a level. So if you had something like this is like a great way to really illustrate what this is for. You're doing BFS for this. We go through the first level, which is this. Then you would navigate through the second level and then through the third. Now let's say these are numbered. Let's say this is 1, 2, 3, 4, 5, 6, 7, like so. Well, if you had to print out your BFS, it would actually print out like this: 1, 2, 3, 4, 5, 6, 7. Because you're going layer from layer, and you're going usually from left all the way to the right. Okay, so that's like the main thing to know for BFS. In terms of searching on the graph, usually you do not want to have anything weighted. In this example, I'm using this graph for to illustrate multiple things. So it is weights. Ignore the weights. It's okay. It doesn't matter. But I'm going to use blue. So I'm going to just start at the first node. Doesn't matter where you start. You will end up with different spanning trees. Does everybody know what a spanning tree is? It's a tree with no cycles. And it covers all nodes. So that is actually really important. So we're going to start with 1, and then we're going to go out. First, let's pretend 2 is towards the left. We branch towards 2. And then we go back to the beginning node. We branch out again. Think of it like vines. It branches out in all directions before going back. Okay, now we have 3. We're going, okay, after you go here, we see, okay, we can claim that node, we claim it. Then we go back. Can you go do the same with the rights? Yes, you can claim 2. Okay, now we go back to the very start, 3. Can 3 claim any more nodes? Yes, it can. We go towards the left. Perfect. We go back to 3. Can 3 get any more nodes and not create a cycle? Yes, it can. It can navigate up to 5. Perfect. Okay. Can 3 claim any more nodes and not make a cycle? We would think okay, 3 can go here. No, because that would create a cycle. So now we go back to the very start. We go back to 2. Can 2 get any nodes and not make a cycle? Can 2? Yes. Can 2 claim any nodes and not make a cycle? Well, yes. 2 can get 7. Could 2 have taken this node? No, because it would create a cycle. Exactly. Okay, so we're done with 2, and then we go back. We go to 6 because that's the first thing that we covered with 4, which is covered. Sorry, but 6, can 6 take any nodes and not make a cycle? Yes, exactly. 7. There we go. And then can 6 take any more nodes? No. So then we go to 5. Can 5 take any nodes? No. Now we go to last number, which is 4, which is actually up there. I think that's 4. Let me just try to erase it. Yeah, that's 4. This is 3. Can 4 take anything? No. So then that is your spending tree. Yep.
So like, what's the order we're supposed to go in?
Honestly, I was taught left to right.
So,
So down to up. In this case, like if you switch this graph, like imagine this graph was written on this paper. It's like, it's left to right. You would turn it this way. Okay, just, he will probably specify where you start and what the order is. But in my head, I'm turning this graph this way. I'm just flipping the page and saying that this is the right, this is the left, this is the right. Any other questions? Okay. He might ask you BFT. He might ask you all these graphs, actually. I won't lie, during my exam, I had all these graphs, everyone. And they were pretty simple and pretty important. They were like 3 marks. So you guys will be fine. Okay. Now we're covering depth first search. Depth first search is really different from breadth first search because depth first search, you take one node and you explore all nodes you could possibly explore without forming a loop, and then you go back. So I'm just going to add one node here just to illustrate it further. We're going to name this one 8 because we have no 8s, just for example. Okay, we're going to start at 1. Okay, and we're going to go towards the left. We're going to treat, this is here, let me just write, this is left, this is right. We're going to go towards 3. Is there any node that 3 can explore? Yes, we go towards the leftmost node, which is 6. Is there anything else that 3 can explore? Or 6 now can explore? Yes. Can explore 7 without creating a cycle. 7 can explore 5 without creating a cycle. 5 can explore 4 without creating a cycle. 4 can explore 2 without creating a cycle. Can we expand from 2? No, because it would create a cycle. Okay, so now we go back all the way to the start. That's why I drew this note, so it kind of illustrates what you do. You go back all the way to the start to 1, and you see, can 1 explore anything? Yes, 1 can explore 8. So your breadth first search would do that way. Most likely, he might give you like maybe a multiple choice question that says something like, okay, if you have a tree and you do breadth first search, what numbers would you get first? And he might number the tree like 1, 2, 3, 4, 5, 6, 7. What order? Well, it's 1, 2, 3, 4, 5, 6, 7. And if he says do DFS on this tree, well, think, I'm going to do DFS. What is the depth first search? We're going to travel all the way through. And then we're going to go back. And then we're going to travel all the way through. And then we're going to go back and travel all the way through. Like go back there. So in terms of this, it would be 1, 2, 4, 5, 3, 6, 7. You can mentally go through it again later if you want. This is just to illustrate like the same thing, but now in a more streamlined example with actual numbers that might appear in a multiple choice. Okay, perfect. So now going forward. So now we're done breadth first search, depth first search. That's like what we started with, and we became more advanced. Now we have Dijkstra's, Prim's, and Kruskal. Which one should I cover first? Should I leave Dijkstra for the end? Just as like I'm not like fully done yet, but Dijkstra, Prim, Kruskal, you say?
Go Prim first.
Prim, okay, perfect. So Prim is similar to Dijkstra in that you have to calculate the weights of each path. Unlike Dijkstra, Prim just takes the edges and it has no addition or any other method. So we're gonna start, usually it tells you which node to start at. We're just gonna start at 1. Sorry, this image is a little blurred, but it's good enough. We start at 1 and we see what's the least weighted edge that we could take. Well, that would be 2, because either we have take 2 or 4. We choose to take 2. So now we have 3. What's the least weighted edge we can take? Now we have more numbers to choose from. We have 4, 1, 8, and 10. Well, 1 is the least numbers, or like it's the lesser of the bunch. So we take 1. Now we navigate 2. Okay, what can we navigate? That's the least. We have 7, 5, 8, and 4. Why don't we take 4? Why don't we do this? Exactly. So out of the bunch, what do we choose? 5. Exactly. We go here. Okay, now you have access to way more. Now we have, okay, we can take this path. You could take this path. You could take, oh no, we can't take this path. It's closed now because it would create a cycle. We can also take this and this. Which one do we go through next? Yeah? Okay, perfect. We take the 4th. Now, on your exam, he might have 2 tables. He might say, okay, right? He might give you actually just a Q. And he might say, in relation to this Q, which one would you take? There's 2 ways to do it. You take the Q and you make a graph, which is what I did, because it's just much simpler. Or you navigate through the Q. I'd say create the graph, which is easier. And then you're gonna have another like list. You're gonna list which ones you've taken. So you've taken 1, or like which nodes you've taken. So 1, 3, 2, 5, 4. Okay, what's the next order? Well, we have 2, which we can take, which is the least. So now we can navigate it to 6. And then what else? We take this one, which is 3, 7. And that's it. That's Prim's. I'm gonna write that down, Prim's. Perfect. Does that make sense to everybody? Yeah?
What if you have 2 edges of the same way?
If you have 2 edges the same weight, okay, that's perfect. So, I'm gonna do this in red or pink, whatever. So you're saying like if I had, sometimes it doesn't matter. Like in this case, did I have, yeah, I had 1 here and I had 1 here and it did not change anything. Let's say I had 1 here and I also had 1 here. Well, you would just take the, like in that case, I don't think Kareem would be too rough on which one you ordered first. But if I had 1 here, instead of 5 going there, I'd have 5 going here and this going down. But in terms of like the ordering, I don't think he's gonna be that like, he's gonna be like, oh no, you didn't do this first, therefore -4. No, most likely he's gonna slow market correct. Any other questions before I move on? Okay. Oh, yeah, yeah.
After you're done running through the other 2 algorithms, can you show us how to find how many minimum spanning trees of how?
Yeah, for sure. Find minimum spanning trees. Okay. And yeah, I have 2. Okay, let's go. Perfect. Okay, so now we're gonna do Kruskals. Kruskals is like the easiest one of the bunch. I think the hardest part for me during this exam was remembering which one was which Kruskals. Kruskals, I just think of glass. And if I think of glass, I don't know how I relate it to this algorithm. I just think of glass whenever I hear Kruskals. It's okay. As long as you find out a way to know it, you're fine. So in terms of Kruskals, everything is in its own cloud. So you can take any node that you want from the graph. I forgot to mention, but Prims, the reason why we could only select from what we've already like seen before, like when we were right here, we could only select what was attached to these nodes that we covered. It's because like it belongs in its own cloud. We can only reach what we've seen or what we know the edges of. And it's highly dependent on how the algorithm works. But yeah, that's why we can only consider 7. That's why we could only consider 7, 5, 8, and 10. But in terms of Kruskals, everything is in its own cloud. That means you consider everything at once. So you have 2, 4, 5, 7, 6, 8, and 1, just to illustrate the cloud. So which one do we pick first? Now, this is also where your question comes in hand, because there's 2 things that you can start with first. You can start with 4 and 5, or you can start with 2 and 3. It does not matter which one you start with, you will most likely produce the same spanning tree. Well, let's say we start with 2 and 3 just to keep things simple. Okay. What's the next thing we start with? Yeah? Sure, yeah, exactly. 5 and 6. 4 and 5? Oh, yeah, exactly. Yeah, you're right. 4 and 5, and then the next one would be 5 and 6. You can see that we're taking nodes off the graph at random in terms of the edges. We're just taking from the least amount of edges to the most. What's next? I'm picking on you today, I'm sorry.
1 to 3.
1 to 3. Let me see. Yeah, exactly. Now, why don't I choose 4, 2 to 1? Because that would create a cycle. I think we get the point now. So I'll stop iterating through it. Okay, what's next? Anybody?
6 to 7.
Exactly, 6 to 7. And then after that, you would take 5 to 2. I mean, yeah, 2 to 5. And then that's it, we're done. That's how easy Kruskal is. You barely need to look at the graph.
Why would you take 2 to 5? Would that create a cycle?
Where is the cycle?
Didn't we already visit one?
Okay, so this is how you can easily check if there's no cycle. A cycle is when you have something that's connected on all sides. This is not connected, this is not connected. So if you drawn out this, like this graph, you'd have something like this. None of these can hold water. I mean, they could try, but it'd just fall if you spin it around in a circle. Therefore, there is no cycles. Good. Yeah, perfect. Still does not make sense.
No, I'm just unsure because why would we visit 5? Because then we already do that before.
We visited 5. Okay, we're still creating a spanning tree. So in order to make a spanning tree, every node has to be connected to each other, right? If we did not visit 5, this would not be a tree anymore. It'd be 2 trees or a forest, which is also something you should know. You should know the difference between a tree and a forest and a forest and a tree. Have you guys heard of those terms? Yeah? Okay. You should cover those because it is important. Like this single node is a forest and it's a tree, I'm pretty sure. Yeah, but does that make, yeah?
So there has to be a path between every.
Yes, exactly.
So that's why we wouldn't do 1 and 2 because there's already.
Exactly. Exactly. There has to be a path within every node. Okay. Okay, now it's Dijkstra, the thing is probably maybe the hardest graph you cover, but it's not really that hard. I'll make it seem easy, hopefully. You start at 1, and it's the same thing as Prim's. As you collect more nodes into your set, these nodes have a sort of cloud, and you can visit any node that connects to those nodes. So you will start with 1, and these are all infinity. Because you have not discovered them, you don't know their weight yet. Okay. When we start with 1, we can update 2 and 3. 2 is now equal to 4, which is the weight of its edge, and the weight of its previous edge. And the previous edge was 0, so therefore it's just 4. 3 is now equal to 2, like in terms of its weight. So what do we travel to first? Well, we travel to 3 because it has the least amount of weight. Okay, and now since we travel, we update all other nodes. We know that this node now is not infinity. It's 2 plus 10. So it's the weight of the edge plus the weight of the node that has traveled to it. So it's 10. What else can we update? Well, we can update this path, which is now 2 plus 8, which is 10. This is 12, sorry. This is 2 plus 8, which is 10. Okay, what else can we update? Well, this is now 2 and 3. Since 2 and 3, so it's 2 plus 1, which is 3. It's less than 4, so we can also update this to 3. Okay, and can we update anything else? No. What path do we take? We take the least weighted node, which is actually 2. Okay, now we continue. We can see if we can update 3 plus 7. That's now 10. Anything else? Well, this is 3 plus 5. 8 is less than 10. So we also update this to 8. Anything else that we can update after we capture this node? No. So now we continue. What is the next node that we take? Okay. She said no, thank you. So it's your turn now. I'll give you a minute. Hint, it's the lowest number on the chart.
5.
Exactly. You would take 5 first. Right there. Okay, now that you captured 5, you're going to update all other nodes surrounding it. Well, 1 plus 8 is now 9, which is less than 10. Okay, 8 plus 6 is now, I'm pretty sure it's 12. 14, thank you. Okay, I just can't do mental math anymore. But you now we remove the infinity and we say it's 14. Yeah, it's 14, of course. Okay, what else can we update? We have 2 and 12. Or yeah, 2, yeah, now that's 10. And then can we update anything else? No. So now we consider 10, we consider 9, 14, and 10. What do we take? I pick on somebody random, you.
Me,
Yeah,
I think you would pick 6.
node 6. There's one less that's here. It's 4.
Oh,
It's okay. No, you knew that, don't worry. Okay, you take 4. Can we update anything else? No. What do we take next? Random guy, you. 10. 6? Yeah, exactly. Which is equal to 10, of course. Okay, can we update it? Let's see. Well, this node was 8, 2. Now it's 10. 10 plus 3 is actually lower than 14. So now this is 13. So in terms of, since it's 13, we can travel to it. So he might ask you, what is the total weight of all the edges that you've traveled to? What would you do? Well, you would calculate the weight, which is now, so if I put it on the side, it's going to be 2 plus 3 plus, I think this is 8 when we traveled to it, 10, 9, and 13. You could have gotten stuck if you did not update this node. It would have been 1 greater than the value. And then I'll leave you to calculate that. Okay. Any questions on this? Yeah?
So what is the bonus path? Or what is the, like, the weight you were talking about?
Oh, I told you guys to calculate it because, I mean, it's 10, 10. I can do this mental math, sure. 10, 10, remove this, 13, 13, 13, 26, 26 plus 9. Isn't that 35?
Oh, so that's all of that.
Yeah, exactly. So basically, as you go through on the side, like you will have a table. On the side of the table, you would, as you go through the graph, you would see which weight you've traveled to and you would write it down on that table.
Okay, and you just add all those.
Exactly.
I just have one more question.
Yeah, for sure.
When we went from 5 to 4,
Mhm.
the weight didn't change when we went from 5 to 6.
Okay, yeah, okay, so this was 8, right? Before, if I remember correctly, this was 10.
It was 9.
Oh, no, before we updated, it was 10. And then this one was, I think, 12.
Yeah.
Okay. Since taking this edge would lead to a less value, like in terms of 10, 9 compared to 10, 9 is less. That's why we updated this edge. If this edge was like, okay, if we change something here and then this edge was like 7, you would not update it. But because it was less, we updated it. And in terms of here, 8 plus 2 is 10, and 10 is less than 12. So that's why you also update that to 10. But you're right, sometimes you don't update it. Like let's say, since this was 3 when we updated it, let's say this path was 2, just as a closer example. Okay? Or 2, let's say this is 2.5, whatever, just to make sure like the order is correct. You would actually not take this path, because that would mean this would be 3.5, which is greater than 2.5. Instead, you would go and travel there. So you have to like see, is it less than? Is it greater than? If it's less than, then you're good. Do you guys have questions or are you good? Okay, perfect. Yeah?
Is the weight, like, how do you get the weight?
Okay, the weight is the node that you last traveled to, weight plus the edge. That's like you're going to.
So it's different than getting anyway for Prim and Kruskal.
It's yes. Okay, for Prim, this is a good thing to illustrate. For Prim, it's just the weight of the edge. You don't do any calculations.
Okay.
For Kruskal, you're just taking the one you're taking the least weighted edge to the most. You don't even consider like a path necessarily when you're talking about the weights. But for Dijkstra, it's the only thing you need to calculate. You need to recalculate the weights every time.
Okay, because I remember in the assignment, they only asked for the weight of Prim and Kruskal.
Yeah.
They're, like the same, because you'll count the edge, but I didn't know it was for Dijkstra, so I was confused if it was the same,
Mhm.
or it was the calculated.
That's good.
How would you do it for Prim?
Okay, Prim, I can do it up here. So Prim, so okay, let's see, do I have another graph? No, I don't. Okay. It's okay, I'll just redo Prim pretty quickly. Let me just, I guess I can just illustrate it with another color. Let's go pink, sure. So for Prim, imagine these lines don't exist anymore. You're gonna be considering, so we're starting at 1. Actually, let's start at a different thing, just for fun. Pick a number. 5, okay, we're starting at 5. Okay, next to 5, we have 1, 6, and 2. Which one's the least amount? And 5, we also have a 5 here and an 8. That's within our cloud. That's the edges we can see. Which edge do we take? We take the one that's least. So we take 4. 4 is now a part of our cloud. This is like the difference between that and Dijkstra, is that we don't update any other edge. This edge is still 5. This edge is now, well, we can see this edge now. It's 7. And that's it. What's the next one we take? Well, we're done going from 4 to 5. So now we go to the least amount, which is 6. Right here, because that has a weight of 2. And then we see here, this is 3. We go here because that's the next highest, least weight. Okay, now we compare. Can we take 6? No, because that would lead into an edge. Now let's see what else. We have 5, 6, and 8. Or we have 5, 7, and 8. So we take the one that's weighted as 5. We go through. You see how we're not updating every time we go through? That's only for Dijkstra.
And so then the total weight of this, you just calculate the edges.
Just calculate the edges.
So it would be like 1 plus 2 plus 3
Yeah,
plus 5.
so it would be, yeah, exactly. I can actually calculate it with like the example we have.
Yeah.
Really quickly. So before all the pink stuff, we had 2 plus 1, get it? 2 plus 1 plus 5 plus 2 plus 3 plus 1 plus 5 plus 1 plus 2 plus 3. And that would be, this would be 3 plus 5 plus 5, 13. Yeah,
Just letting you know it's 30 minutes before we.
have to bounce. Okay, I think I have like two things quickly to cover. So I think we should be good. Okay. Questions, leave them to the end. I'm gonna quickly go through these because hashing is very important. It's like one of the things you covered. I was there in the lecture when you covered it. So let's go. Okay. What is the order of the keys in this table? It's asking, okay, regarding the order of insertion in this table, which answer is correct? We have quadratic probing. Quadratic probing means we have an HK is equal to HK plus I, which is going to be quadratic mod M. And M is the size of the M is the size of the array. In this case, it would be 7. And it gave you it here, which is nice. So let's just go through quickly. We know that this 1 could not be first. Why? Because 1 mod 7 is 1. If 1 was first, then it would have been in 15 slot, but it's not. Okay, let's see what came first. So we know 1 is not first. How about 15? We know 15 must have been first because 15 mod 7 is 1. Yeah?
For quadratic probably, is it the I squared?
Yes. Oh, well, yeah, the I squared each time. Yeah, exactly. But we know 15 is not first. We know 15 is first because 15 mod 7 is equal to 1. So we know that 15 came first, and then most likely second would be 1, let's just say. Third, how did we get, so this is also, okay, between 15 and 5, we can't tell which came first because 5 mod 7 is 5, 15 mod 7 is 1, and it's in its respective indexes. Okay, that doesn't matter. The questions are really asking what is the last to be inserted. So let's see. We know that, let's consider 8, because 8 we haven't talked about. Okay, so 8 mod 7, what is that? 1. Okay, we take that value, 1, and we continue to just add a quadratic to it. So now it's just 1 plus 1 with mod 7. What is that? 2. Is 8 in 1 or 2? No, then we continue. So now it's 1 plus 2 mod 7, which is 1 plus 2. I'm pretty sure, no, actually, wait. 1 plus 2, I'm pretty sure, and then you quadratic, right? Because it's 1, and then it's 1, might be 4. Give me a second. It's 1. Actually, I feel like it's 1, 2, 4.
Yeah.
Yeah, okay, that's how I like learned 1, 2, 4. Okay. So you add 1 and then you quadratic. Okay. 2. So 3 mod 7 is 3. I'm just gonna do the next one because you know, okay, 3 mod 7 is 3. And 8 is in the 3 spot. Actually, I think Paul's right. Yeah. Yes, exactly. I think Paul was right when it's 4.
Yeah.
Because
I squared.
exactly, because it's 2, I goes from 0, 1, 2. So it's 2 squared, which is 4. So now it's 5. We go to the 5th index and we know that 8 is not there. So we continue going. I plus 3 squared, which is 9, or which is 9 plus 1. Okay, so it's 10. 10 mod 7. Yeah, exactly. And we know that 8 is in the 3rd index. Since 8 is not in the 5th index, because 5 was there, we know that 5 was not the last thing inserted. So therefore, we can claim that 8 wasn't the last key inserted. This is also in your Kahoot. I was there during class when it was taught. Okay, considering the following hash table, you have this function, k mod 7, and it's linear. What is the average number of probes for A? We're searching for an existing key in this table. For searching an existing key in this table. Okay, let's see. Well, if you're searching, let's say you're searching for 15. How many probes would you need? You need 1 probe. Why? Because 15 mod 7 is 1. And you know that 15 is in the 1st position. Perfect. Let's say you're searching for 1. How many probes would 1 take? 2. Because 1 mod 7 is 1. Okay. 1 plus 1 is 2. 2 mod 7 is 2. And it's in the index 2. And this is another key thing to note. It's linear probing. That means you're just iterating through 1 by 1. So this would need 2 probes. probe. Yeah, I think that's probe. Yeah, okay. Now, how about searching for 8? Well, let's see. 8's not in the first index, right? Because 8 mod 7 is 1. 1 plus 1, 2. 2 mod 7 is 2. It's not in the second index. 1 plus 2, 3. 3 mod 7, 3. 8 is in the third index. So it takes 3 probes. Okay, and then 5. Well, 5 mod 7 is 5, and it's in the fifth index. So it takes 1 probe. Then you add the total together and you divide it by how many are in the array. So or the hash table. So it's 1 plus 2 plus 3 plus 1, which is 3 plus 3, which is 6 plus 7. So it's 7 divided by 4. Now 7 divided by 4, you could treat it like 8. 8 divided by 4 is 2, or you can treat it like 6 or like something less. But it's between, we know it's not greater than 2. We know it's not less than 1 because 7 is greater than 4. So it is B. Just giving you some examples of how you can calculate it. You can just obviously look and say, okay, it's between 1 and 2. But just in case if you guys don't know math, that is there.
Very good. What was the answer for the quadratic formula question?
It's 8 was the last key to be inserted. Okay. Suppose you insert element 2 in the table given in question 11 using linear probing. After this, you search for 3. Okay. How many table positions must be probed? Now we're using linear. Perfect. So let's say you insert 2. Well, 2 mod 7 is 2. You can't fit in index 2 because 1 is taking it. So now you add 1. So now 2 plus 1, it's 3. 3 is taken. 2 plus 4, or wait, no. 2 plus 2, sorry. It's 4. 4 mod 7, it's 4. So then you use index 4 with 2. Okay, one thing I should point out, the professor told me that some people, they have a function, oh no. That's good, I just need to write this down. Some people, they have a hash function, whatever, with like hk plus I mod. They have something like this. And they, let's say your hk is like 10. And you're 10 and you're modding with 12. Okay, when you're done this step, plus 0 mod 12, you would take this 10 and you would add it every single time, right? You don't, like, this is better if you have like, let's say this was 13. Instead of using 13 with every iteration, you would instead use 1, because 13 mod 12 is 1. So when you're going forward, just use 1. It's the same as using 13, but that's just a lot of math. And you kind of want to be quick on this exam. So yeah, if you guys are confused on what I mean about this, I'll illustrate it deeper, like in more depth later after the session. Okay, so now we're gonna search for 3. Well, 3 mod 7 is 3. So we're searching in the third index. 3 is not there, so we continue. Linear probing, we plus 1. We search at 4. It's not there. We continue. Search to 5. Not there. Search at 6. Okay, we see 6 is empty. And since 3 is supposed to be in 6, that means 3 does not exist in this hash. How many probes did we use? 4. And I think that's your answer. 4. Perfect. Now just quickly going through sorting algorithms. Most likely you will have a question similar to this on your final. Let's start. Okay. Insert sort, merge sort, and quick sort. What is the worst time complexity? Well, you can just go through. You know the insertion sort is quadratic. Therefore, it's big. If you see this, this is theta. It's similar to O. Just like don't like have a headache thinking about it. You got this. Okay. You know that it's n squared. Now you go to merge sort. Well, merge sort, if you don't know, it splits it into a tree and then it iterates through the tree to find it. It's divide and conquer, so we know it's n log n. And then we look at quick sort. What's the worst time complexity for quick sort? Average case, we know that it's faster than insertion sort, but worst time complexity, we know that it's, we know that it's n squared. Therefore, the answer is D. Does that make sense? Most of the theory, like, you should know all like the, like whether you, so like a PQ with a heap, PQ sorted, or like heap that's sorted, heap that's non-sorted. There's this one table that's beautiful. You should know that. Yes?
Could you just go back and go the question to each of them again, the worst case one?
Yeah. The worst case for insertion sort is ON. Worst case for bubble sorts, ON. Worst case for quick sorts, ON squared. Sorry, whenever I said it, I meant squared. Worst case for merge sorts, N log N. What else? Yeah, so, sorry, I'm just like running out of time, I think. But here, I'll write it down. Cert ON squared. This is the same for bubble, which is the same for quick. Merge, it's divide and conquer, so it's ON log N. If they ask you, what is the fastest possible time an algorithm can take? It could be a trick question, but O log N is like the fastest algorithm sorting we have. And this is like a general case. There are specific questions that you can sort, and you can use another complexity. If they ask you, you have a random divide and conquer algorithm. What is its worst time complexity? N log N. Divide and conquer is usually always N log N. Okay, just gonna go quickly through merge sort. This is the last thing I'm covering. You should probably do something similar for bubble sort, quick sort. Take a table and sort through it, and then see if you truly understand what's happening in place. Oh, this is another good question. Can all of these be done in place? Insertion sort can, quick sort can, merge sort can, I'm pretty sure. Oh no, merge sort cannot. That's it. Merge sort cannot be done in place. Heap sort can be done in place. Just like all the Kahoot questions that we've got, like they're really helpful to review. Okay, we're just gonna quickly do merge sort on this list. So merge sort, it's divide and conquer. All you do is split it in half. And then you keep splitting it in half until you can compare two things together. So the first thing, you have split this in half, 30, 10, 50, 20. 15, 7, 2, 12. If you're given an odd number of indexes, just split it. Don't split it like directly in half. Like make one node at the end. It's okay. You will figure out how to compare it once you get to the end. It's always broken down. Okay, so now you have to split this also in half. So now you have 30, 10, 50, and 20. And then you have 15, 7, 12, and 2. Okay, are you done yet? No, you have to continue splitting. You split until you reach like a base case, which is if you have no nodes or 1. So you continue splitting. Now you have 30, 10, 50, 20, 15, and 7, and 2, and 12. Okay. Now you compare your neighbors together. So you compare 30 and 10. We're gonna sort from least to greatest. So 10 would be here. 30 would be here. Okay, you also compare these two together. 20, 50, you compare these two, 7, 15, and this would be 2 and 12. This remains the same. I'm gonna just quickly erase this bit. Okay. Now you go through. Now these sections are together. You're just gonna build your whole again. You have 2 iterators and you're iterating through each half and you're making it into a half, like you're combining. This is the combining step. This is why this is the O log n. This is where you get to the n. That's why it's like O n log n. Okay, So now we have 10, 30. Okay, we have two iterators pointing at each of these. And we're comparing from left to right since it's sorted. Is this the greater, like which one's the least? We know that 10 is least, so we continue. This moves there. We compare 10, 30 and 20. We know 20 is less than 30. This moves. We compare 30 and 50. We know 30 is less than 50. Okay, then you continue going here. You have 2 pointers. You're comparing 2 and 7. 2 is less than 7. Okay, this moves. You're comparing 7 and 12. 7 is less than 12. This goes. You're comparing 15 and 12. 12 and 15. And then the last step is you're combining. You have 2 big iterators, and I'll do this in a different color so you can see it clearly. Okay. Perfect. Okay, let me just. So you have 2 pointers, one here, and you're going through. You're comparing 2 and 10. 2 is less than 10. Write it down. This pointer moves to the next element. You're comparing 7 and 10. 7 is less than 10, so you also write 7. This pointer moves down. You're comparing 12 and 10. Well, 10 is less than 12. Then this pointer moves. You're comparing 20 and 12. Well, 12 is less than 20. Then you're going here. You're comparing 15 and 20. 15 is less than 20. And then you just do, then you can just add on that last half of the list because it is ordered. I broke it down in a lot of steps just so you can kind of see the process. Most likely during the final, he's going to give you just a big chart, like a big chart with like, he's going to indicate kind of what split you need, how many lines you should show, fill up all those lines. And if you have to use more, do so. I think I have what this question would be worth, 3 points. So he's probably going to want to see like the splitting and the iterative step. But yeah, does everybody understand how merge sort works? Okay. Any questions relating to anything that we've covered? No? Okay. Well, thank you guys for your time. This has been a great session. Thank you. I will post the video to my YouTube channel, Preppers Up, and I'll also post it to you guys' channel. I'm thinking, yeah. This will be a part of my Discord. If you don't have access to my Discord, let me know. I'll also give it to you guys to distribute.
We'll be posting it on our Instagram as well.
Yeah, perfect. You guys will have my notes, review it. It has everything that is covered. What else? I wish you luck. You got this. Honestly, the final was really easy. Like when I took it, Kareem told me yours is harder, but I've seen it and it's not that hard. So you're good. If you, yeah, if you guys know this, no. If you guys review my review and go in deeper, you got this. Thank you very much. Thanks for the help, helping me along the way. It's been a while since I've done this. Yeah, this is Prepper Zep, Joey. Yeah, thank you guys in Zoom who are watching. I hope it didn't take too long. I probably did. That's okay. Hopefully this recording saves.
Thank you, Joey.
No problem.